Did James Webb just discover what triggered the Big Bang? Nothing. 13.8 billion years ago, the universe exploded into existence. What caused it? Until now, we only had theories, educated guesses based on cosmic clues that have survived across billions of years. Scientists have spent decades chasing the first moments of time, piecing together whispers of the universe's birth from faint light and subtle patterns. What if the James Webb Space Telescope has just glimpsed that elusive moment? Did James Webb just discover what triggered the Big Bang? The Big Bang left fingerprints everywhere. The cosmic microwave background preserves the heat of the newborn universe. The distribution of matter reveals how energy and gravity shape space. And the first light from ancient stars, rayonization, carries the echoes of creation. JWST isn't just a telescope, it's a time machine, peering back further than Hubble ever could, capturing light from the very first galaxies and stars, offering humanity its closest look yet at the universe's original spark. Every observation could be a clue, every faint glow a piece of a puzzle that might finally answer the question, what triggered it all? Before anyone talks about discoveries, signals, or clues from the edge of time, the story has to start much earlier, long before James Webb ever opened its golden mirror in space, because this telescope was not born from a single idea or a sudden breakthrough. It was shaped by decades of frustration, ambition, failed designs, political arguments, engineering limits, and a global effort that pushed space science further than it had ever gone before. The idea that became James Webb began in the late 1980s, when astronomers started realizing that Hubble, powerful as it was, would never be able to see the very first light of the universe, because the earlier stars and galaxies were hidden behind distance, expansion, and time itself, with their light stretched so thin and red that optical telescopes could barely sense it. And this gap in observation mattered deeply, because without seeing the universe close to its beginning, scientists were forced to rely on theory instead of evidence when talking about how everything started. NASA scientists began planning something radical, not just a bigger telescope, but a telescope that could see heat instead of light, something that could catch the faint glow of objects formed only a few 100 million years after the universe came into existence. And from the start, it was clear this would not be a normal mission, because no telescope had ever been asked to operate so far from Earth, stay so cold, and measure signals so weak that even a human breath would overwhelm them if the instrument were nearby. The original concept was called the Next Generation Space Telescope, and even at that early stage, engineers knew the challenges would be extreme, because infrared astronomy demands cold temperatures, perfect alignment, and total darkness, which meant this telescope could not orbit close to Earth like Hubble. It had to travel far beyond the Moon to a place called the second Lagrange point, where gravity and motion balance in a way that allows a spacecraft to stay stable while facing deep space. Delays followed almost immediately, because every part of the design pushed existing technology past its limits, from the folding mirror that had to fit inside a rocket to the sunshield the size of a tennis court that had to deploy perfectly in space, to detectors that needed to stay colder than anything ever flown before. And each delay added years, cost, and doubt, while critics questioned whether the telescope would ever launch at all. The project survived because it was no longer just NASA's telescope. It became a shared mission between NASA, the European Space Agency, and the Canadian Space Agency, with each partner contributing instruments, launch support, and expertise, turning James Webb into a truly international observatory built by thousands of engineers and scientists who knew that failure was not an option, because there would be no repair mission, no second chance, and no astronauts waiting nearby. When James Webb finally launched, it carried more than hardware. It carried expectations built over 30 years, because this telescope was designed not just to look deeper, but to answer questions that had been locked behind time itself, including what the universe looked like when it was young, how the first stars formed, how the first galaxies assembled, and whether there were signs of physical processes that could point back toward the moment everything began. At the heart of James Webb are its instruments, each one built for a specific role, each one working together like parts of a single eye. And the first of these is NIRCam, the near-infrared camera, which acts as Webb's main imaging system and its primary scout, capturing stunning images of distant galaxies whose light has travelled for more than 13 billion years, stretched into infrared wavelengths by the expansion of space itself. NIRCam does not simply take pictures, it measures brightness, structure and shape across multiple infrared bands, allowing scientists to identify ancient galaxies, estimate their distances and determine which targets are old enough to belong to the universe's earliest eras. And when NIRCam sees a faint smudge of light where no galaxy should exist according to older models, that image becomes a doorway into deeper investigation. Next is NIR-SPEC, the near-infrared spectrograph, which turns light into data, breaking it apart into its component wavelengths, revealing chemical fingerprints hidden inside ancient photons. And this matters because light carries information about temperature, motion, composition, and age, allowing scientists to tell whether a galaxy contains heavy elements formed by earlier stars or only simple hydrogen and helium left over from the early universe. NIR-SPEC can observe hundreds of objects at once using tiny shutters smaller than grains of sand, opening and closing to isolate targets across the sky, which allows it to map early galaxy populations with incredible efficiency. And when scientists analyze this data, they are not guessing, they are reading the physical record left by the universe itself. Then there is MIRI, the mid-infrared instrument, which sees even longer wavelengths than NIRCam and NIR-SPEC, pushing deeper into dusty regions and colder objects that would be invisible to other telescopes. And MIRI is especially important for studying the earliest star-forming regions, because the first generations of stars formed inside dense clouds of gas and dust that block visible light but glow faintly in the infrared. MIRI operates at temperatures colder than any instrument ever flown, using cryogenic systems to reach levels where even its own heat does not interfere with observations. And this extreme cold allows it to detect signals that are unimaginably weak, signals that may come from galaxies forming only a few 100 million years after the universe began expanding. FGS and NIRS complete the instrument suite, with FGS acting as the telescope's stabilizer, locking onto guide stars with extreme accuracy, so Webb can hold steady for hours or days without drifting, because even the slightest movement would blur signals from the early universe, while NIRIS specializes in detailed measurements of exoplanets, stellar populations, and faint structures, adding another layer of precision to Webb's view of cosmic history. All of these instruments serve a single scientific goal: to observe the universe during its earliest stages, when the first stars ignited, when the first galaxies took shape, and when light first began to fill the darkness left behind by the Big Bang, because understanding these moments is essential to understanding everything that followed, including the structure of the universe today. Infrared light is the key that makes this possible, because as the universe expands, light traveling through space stretches along with it, shifting from shorter wavelengths into longer ones, a process known as redshift. And the farther back in time an object is, the more its light is stretched, until visible light becomes infrared, and ultraviolet light becomes invisible to optical telescopes entirely. Hubble could see some of this redshifted light, but its instruments were not optimized for it, and its mirror was too small to collect enough photons from the faintest sources, while James Webb was designed specifically to capture this stretched light, using a mirror more than 6 times larger than Hubble's, coated in gold to reflect infrared wavelengths with extreme efficiency. This difference changes everything, because detecting early galaxies is not about sharp images alone. It is about collecting enough light to rise above the background noise of space. And the early universe is faint, not because it lacked energy, but because its light has traveled for billions of years, losing intensity and stretching along the way. Compared to Spitzer, which also observed in infrared, James Webb operates with far higher resolution, greater sensitivity, and a wider wavelength range, allowing it to see structures that Spitzer could only hint at. And while Spitzer revealed that infrared astronomy was essential, Webb turns that insight into direct observation. Other observatories contributed pieces of the puzzle, from ground-based radio arrays to cosmic microwave background satellites, but none of them could directly image the first galaxies or analyze their light in detail, leaving a gap between theory and evidence that James Webb was built to close. The technological leap represented by Webb lies not just in size or distance, but in precision, because every observation requires near-perfect alignment, thermal stability, and calibration, and even a slight error could overwhelm the signal scientists are trying to detect, which is why Webb's mirror segments adjust themselves in space, using motors that move by fractions of a wavelength of light. Every photon Webb captures from the early universe carries information that has survived since near the beginning of time, and measuring those photons requires an instrument quiet enough to hear a whisper across billions of light years, which is why Webb hides behind its sunshield, blocking heat and light from the Sun, Earth, and Moon, creating an artificial night colder than deep space itself. This is why James Webb is often described as a time machine, not because it travels through time, but because it looks so far away that it sees the universe as it once was, allowing scientists to observe cosmic events that happened long before Earth existed, long before stars like the Sun formed, and long before galaxies like the Milky Way took shape. When Webb points toward regions of sky thought to be empty, and instead finds galaxies packed into the earliest cosmic epochs, it raises questions not just about galaxy formation, but about the conditions that existed immediately after the universe began expanding, because the presence, brightness, and structure of these early galaxies carry information about the energy, density, and physics of the universe at that time. Each image, each spectrum, each data set becomes part of a larger effort to trace the universe backward, step by step, toward its origin, not through speculation, but through observation, using light as evidence and physics as a guide. And this is where James Webb's story connects directly to the question of the Big Bang itself. Because if the universe carries memory of its birth, that memory is written into the earlier structures, the first stars, the distribution of matter, and the way light behaves across cosmic distances. And James Webb was built to read that memory more clearly than any telescope before it, not by accident, but by design, through decades of planning, engineering, and collaboration aimed at seeing what had never been seen before. And when a telescope built to observe the first light of the universe starts revealing patterns that do not fully match existing models, the question naturally follows, not as philosophy, but as science, whether those patterns are pointing toward processes that happen closer to the beginning than anyone expected, and whether the universe itself is offering clues, not through theory, but through observation about how everything began. Current Big Bang Theory basics. To understand what scientists mean when they talk about the Big Bang, it helps to remove the image of an explosion happening at a point in space, because the theory does not describe matter flying outward into empty surroundings. Instead, it describes space itself expanding, stretching, and carrying energy and matter along with it from an extremely hot and dense early state. At the earliest moment described by the theory, the universe existed in a condition where all matter and energy were packed together so tightly that ordinary ideas like distance, size, and time lose their usual meaning, not because they vanish, but because the equations that describe them stop behaving in ways that match everyday experience. This earlier state is often called the singularity, not as a physical object that can be touched or seen, but as a boundary in the math, a point where density and temperature become so extreme that current physical laws can no longer describe what is happening in a reliable way. The word singularity does not mean a dot floating in space. It refers to a condition where space itself has zero size according to classical equations, where energy is compressed beyond known limits, and where gravity becomes so strong that it overwhelms every other force. What makes the singularity difficult is not that it breaks the universe, but that it breaks our models, because the equations of general relativity, which describe gravity and the shape of space, work extremely well at large scales but fail when pushed to this extreme beginning. As scientists move forward from that boundary, the theory describes the universe entering a phase called rapid inflation, a brief but dramatic period when space expanded faster than light could travel, not because objects were moving through space quickly, but because space itself was growing at an incredible rate. Inflation is central to modern Big Bang theory because it explains why the universe looks the way it does today, with large regions that appear smooth and uniform even though they are too far apart to have exchanged information under normal expansion. During inflation, tiny differences in energy density were stretched across vast distances, turning quantum-scale variations into the seeds of large-scale structure, meaning the smallest fluctuations became the starting points for galaxies, clusters, and cosmic filaments. These fluctuations were not random noise in the everyday sense. They followed specific statistical patterns predicted by quantum physics. And inflation took those patterns and amplified them, freezing them into the fabric of the universe as space expanded. The speed of inflation matters because it explains why the universe appears flat on large scales, meaning space does not curve strongly in any direction when observed across billions of light years, a feature that was puzzling before inflation was introduced. Without inflation, regions of the universe now separated by vast distances would never have had time to come into balance with one another. Yet observations show that temperature and density are remarkably consistent across the observable universe, a consistency inflation naturally produces. As inflation ended, the universe did not stop expanding, but it shifted into a slower, more familiar expansion governed by radiation, matter, and later dark energy. And during this transition, enormous amounts of energy stored in the inflation field were released. This release of energy filled the universe with particles, radiation, and heat, creating the hot early state often associated with the Big Bang, a time when the universe was dense, bright, and filled with energetic interactions between fundamental particles. In this early phase, the universe was too hot for atoms to exist because electrons could not remain bound to atomic nuclei, meaning matter existed as a plasma of charged particles constantly colliding with photons, the particles of light. Photons scattered endlessly off electrons, preventing light from traveling freely, making the universe opaque, more like the interior of a star than the empty space we see today. And during this time, energy and matter were tightly linked. As the universe expanded and cooled, a crucial transition occurred when temperatures dropped enough for electrons to combine with nuclei, forming neutral atoms for the first time, a process known as recombination. Once atoms formed, photons no longer scattered constantly, allowing light to travel freely through space. And this moment released a flood of radiation that has been traveling ever since, stretching as space expands. That ancient light is what scientists now observe as the cosmic microwave background, a faint glow that fills the entire universe and comes from every direction, acting as a snapshot of the universe when it was about 380,000 years old. The cosmic microwave background is not a picture of stars or galaxies, because none had formed yet. Instead, it shows tiny temperature differences across the sky, differences as small as a few parts in 100,000. These temperature variations reflect differences in density present in the early universe, with slightly denser regions eventually pulling in more matter through gravity, becoming the first sites where stars and galaxies would later form. The pattern of these variations is not random. It follows precise mathematical rules predicted by Big Bang theory and inflation, and measuring them has allowed scientists to test the theory with remarkable accuracy. Satellites designed to study the cosmic microwave background have mapped these patterns in fine detail, confirming that the universe began in a hot, dense state and expanded over time, while also providing strong evidence that inflation occurred. The background radiation also carries information about the universe's composition, revealing how much of it is made of normal matter, how much is dark matter, and how much is dark energy, each affecting how the universe expanded and evolved. Dark matter plays a key role in Big Bang theory because it provides additional gravity that helps explain how structures form so quickly, allowing matter to clump together more efficiently than visible matter alone would allow. Dark energy, while not part of the early universe in the same way, affects the later expansion, shaping how the universe grows over billions of years. But the early universe described by the Big Bang was dominated first by radiation and then by matter. The simplicity of the early universe is one of its defining features, because at the highest energies, forces that are separate today may have behaved as a single, unified interaction, although this remains an area of active research. As the universe cooled further, fundamental forces separated, particles gained mass, and the familiar building blocks of matter emerged, setting the stage for the formation of stars hundreds of millions of years later. What makes the Big Bang theory powerful is not that it explains everything, but that it makes clear predictions that can be tested through observation, from the expansion of galaxies to the temperature of background radiation. The expansion itself was first inferred by observing that distant galaxies are moving away from us, with farther galaxies receding faster, indicating that space is stretching uniformly rather than matter exploding outward from a center. This expansion is built into the equations of general relativity, which describe how mass and energy shape space and time. And when applied to the universe as a whole, these equations naturally lead to a beginning where density increases without bound as time moves backward. Inflation modifies this picture by inserting a brief phase that smooths and flattens space before the hot Big Bang phase begins, helping resolve problems that earlier versions of the theory struggled to explain. Despite its success, Big Bang theory does not describe what caused inflation or what happened before it, because the physics required to answer those questions lies beyond what has been tested directly, making the earliest moment a frontier rather than a finished story. What remains firmly established is that the universe expanded from a hot, dense state, cooled over time, and left behind observable traces in the form of background radiation and large-scale structure. The cosmic microwave background acts like a fossil, preserving conditions from a time long before stars or planets existed, allowing scientists to study the universe's early state using data rather than speculation. The temperature of this background radiation today is just a few degrees above absolute zero, because the light has stretched along with the universe's expansion, losing energy as space grows. This stretching of light is the same process that shifts distant galaxies into infrared wavelengths, linking early universe theory directly to modern observation. Every measurement of the background radiation adds detail to the picture, refining estimates of the universe's age, size, and composition, and strengthening the core framework of the Big Bang model. The theory continues to evolve as new data arrives, but its central ideas remain grounded in measurable evidence, describing a universe that began hot and dense, expanded rapidly, and cooled into the structured cosmos observed today. Inflation explains why the universe looks smooth on large scales, while still allowing small differences to grow into galaxies, while the cosmic microwave background provides a direct window into that early time. Together, these elements form the backbone of modern cosmology, offering a coherent account of the universe's early evolution that can be tested, challenged, and refined through observation rather than belief. And it is within this framework, built on inflation, early density fluctuations, and background radiation, that scientists search for deeper clues about the conditions that existed at the very beginning, using evidence written into the structure and light of the universe. What James Webb might have observed. When scientists began examining the deepest James Webb data, attention quickly shifted away from familiar galaxies and towards something far more basic and ancient. Structures that appear less like finished systems and more like raw material. Vast clouds of gas glowing faintly in the infrared, shaped by gravity, but not yet fully transformed into stars or galaxies as we know them. These primordial gas clouds are thought to be made almost entirely of hydrogen and helium, the simplest elements created in the first minutes after the universe began expanding, long before heavier elements like carbon or oxygen existed, and seeing them directly has always been one of the hardest goals in astronomy because they emit very little light and are easily hidden by later cosmic activity. James Webb's sensitivity allows it to detect subtle infrared glows from these clouds as they respond to surrounding energy, revealing shapes that stretch across thousands of light years, uneven and clumpy rather than smooth, showing early signs of matter falling inward under gravity, while still lacking the chemical complexity seen in later generations of stars. What makes these clouds remarkable is their timing, because their redshifts place them extremely close to the earliest observable era, meaning they formed when the universe was still transitioning from its initial hot state into a structure-forming phase, a time when conditions were unlike anything seen later. Within these clouds, Webb data suggests regions of intense brightness that do not match the signatures of normal stars, raising the possibility that the telescope is seeing the first generation of stars ever to ignite, known as population 3 stars, objects that have never been directly observed before. Population 3 stars are predicted to be very different from stars today, far larger, far hotter, and far shorter lived, because without heavy elements to regulate nuclear reactions, they would burn fuel at extreme rates, releasing enormous amounts of energy in a very short time before collapsing or exploding. The light from such stars would be dominated by intense ultraviolet radiation, which by the time it reaches James Webb would be stretched deep into the infrared, producing unusual spectral patterns that differ from those of later stars. And some Webb observations show hints of exactly this kind of signal. These spectra lack the chemical fingerprints of metals, showing instead simple profiles dominated by hydrogen and helium interactions, consistent with theoretical predictions of population 3 stars. And while confirmation requires careful analysis, the possibility alone is enough to reshape how scientists think about the universe's earliest energy sources. If these stars are present, they would have played a powerful role in shaping the early universe, flooding space with radiation, heating surrounding gas, and driving rapid changes in ionization, acting as engines that transform the cosmic environment in ways that echo far beyond their short lifetimes. Alongside these potential stars, Webb has detected energy signatures that do not clearly belong to known objects, compact regions emitting more energy than expected for their size, raising questions about whether unfamiliar physical processes were active in the early universe. Some of these signatures appear too intense to be explained by star formation alone, hinting at concentrated energy sources that formed before galaxies had time to assemble fully, possibly linked to early black hole formation or unknown high-energy phenomena. What makes these signals especially interesting is their consistency across multiple observations, appearing in different regions of the sky at similar redshifts, suggesting they are not rare accidents, but features of the early universe itself. These exotic energy signatures may reflect conditions where matter and energy interacted in ways no longer possible today, under densities and temperatures that existed only shortly after the universe began expanding. In this environment, physics operates at extremes, where small differences can produce massive effects, and where energy fields that no longer dominate today may have shaped the behavior of space itself. This leads scientists to ask whether the patterns Webb is detecting could carry indirect traces of the process that drove inflation, the rapid expansion thought to have occurred at the very beginning. Inflation is believed to have been powered by a high-energy field that filled space uniformly, driving expansion while imprinting tiny variations that later grew into structure. And although inflation itself happened far earlier than any direct observation can reach, its effects should still be visible in how matter and energy were distributed afterward. If Webb is seeing unusually early and intense structure formation, it could imply that the initial conditions left by inflation were more energetic or uneven than previously assumed, allowing matter to collapse faster and ignite sooner. The presence of massive stars or compact energy sources so early would suggest that density fluctuations were strong enough to overcome opposing forces almost immediately, a scenario that points back toward the nature of inflation itself. Some of the observed gas clouds show sharp boundaries and directional features, as if shaped by strong radiation or pressure gradients, possibly relics of early energy flows that trace back to inflation-driven variations. These shapes are not smooth or random, but show signs of alignment and coherence across large scales, hinting that the early universe may have retained memory of its initial expansion patterns longer than expected. If inflation produced fluctuations with slightly different properties than standard models predict, those differences would influence how gas collected, how stars formed, and how energy moved through space, effects that James Webb is now positioned to detect. The idea is not that Webb is seeing inflation directly, but that it may be observing the consequences of inflation preserved in the earliest visible structures, written into the arrangement and behavior of primordial matter. Every unusual brightness pattern, every unexpected spectral feature, every early concentration of energy becomes a data point in this investigation, helping scientists test whether existing inflation models fully explain what is now being observed. Some models predict a smoother early universe, others allow for more dramatic early structure, and Webb's data appears to favour scenarios where early energy differences played a stronger role, though interpretation remains careful and cautious. The possible detection of population 3 stars adds another layer to this picture because their formation requires very specific conditions: rapid collapse, intense cooling through limited channels, and strong gravitational influence, all of which depend on the early energy landscape. If these stars formed earlier and more frequently than expected, it suggests the universe moved quickly from expansion to structure, compressing matter efficiently in a way that reflects its earlier state. Exotic energy signatures, primordial gas behavior, and early star formation all point toward a universe that was not gently settling after inflation, but actively reshaping itself at high speed, driven by forces set in motion at the very beginning. James Webb does not tell this story through a single image or a single object, but through patterns repeated across independent observations, patterns that suggest the early universe was far more dynamic than previously imagined. Each new dataset adds detail, revealing interactions between gas, radiation, and gravity that trace back toward the conditions that existed just after inflation ended. The telescope's role is not to guess, but to measure, capturing light that carries information from an era when the universe was still finding its shape and when the energy released at the beginning was still echoing through space. If inflation left behind a specific energy fingerprint, it would influence everything that came after, and James Webb may be uncovering that fingerprint indirectly through the way primordial matter behaves under extreme early conditions. The question of whether this hints at what sparked inflation remains open, but the observation suggests that the universe's earliest visible structures are closely tied to the energy processes that dominated its first moments. By observing primordial gas clouds before they fully become galaxies, by catching the glow of the first stars as they ignite, and by detecting energy signatures that defy simple explanation, James Webb is pushing observation closer to the edge of cosmic history than ever before. What James Webb might have observed. When scientists began examining the deepest James Webb data, attention quickly shifted away from familiar galaxies and towards something far more basic and ancient, structures that appear less like finished systems and more like raw material, vast clouds of gas glowing faintly in the infrared, shaped by gravity but not yet fully transformed into stars or galaxies as we know them. These primordial gas clouds are thought to be made almost entirely of hydrogen and helium, the simplest elements created in the first minutes after the universe began expanding, long before heavier elements like carbon or oxygen existed. And seeing them directly has always been one of the hardest goals in astronomy because they emit very little light and are easily hidden by later cosmic activity. James Webb's sensitivity allows it to detect subtle infrared glows from these clouds as they respond to surrounding energy, revealing shapes that stretch across thousands of light years, uneven and clumpy rather than smooth, showing early signs of matter falling inward under gravity, while still lacking the chemical complexity seen in later generations of stars. What makes these clouds remarkable is their timing, because their redshifts place them extremely close to the earliest observable era, meaning they formed when the universe was still transitioning from its initial hot state into a structure-forming phase, a time when conditions were unlike anything seen later. Within these clouds, Webb data suggests regions of intense brightness that do not match the signatures of normal stars, raising the possibility that the telescope is seeing the first generation of stars ever to ignite, known as Population 3 stars, objects that have never been directly observed before. Population 3 stars are predicted to be very different from stars today, far larger, far hotter, and far shorter lived, because without heavy elements to regulate nuclear reactions, they would burn fuel at extreme rates, releasing enormous amounts of energy in a very short time before collapsing or exploding. The light from such stars would be dominated by intense ultraviolet radiation, which by the time it reaches James Webb would be stretched deep into the infrared, producing unusual spectral patterns that differ from those of later stars. And some Webb observations show hints of exactly this kind of signal. These spectra lack the chemical fingerprints of metals, showing instead simple profiles dominated by hydrogen and helium interactions, consistent with theoretical predictions of Population 3 stars. And while confirmation requires careful analysis, the possibility alone is enough to reshape how scientists think about the universe's earliest energy sources. If these stars are present, they would have played a powerful role in shaping the early universe, flooding space with radiation, heating surrounding gas, and driving rapid changes in ionization, acting as engines that transform the cosmic environment in ways that echo far beyond their short lifetimes. Alongside these potential stars, Webb has detected energy signatures that do not clearly belong to known objects, compact regions emitting more energy than expected for their size, raising questions about whether unfamiliar physical processes were active in the early universe. Some of these signatures appear too intense to be explained by star formation alone, hinting at concentrated energy sources that formed before galaxies had time to assemble fully, possibly linked to early black hole formation or unknown high-energy phenomena. What makes these signals especially interesting is their consistency across multiple observations, appearing in different regions of the sky at similar redshifts, suggesting they are not rare accidents, but features of the early universe itself. These exotic energy signatures may reflect conditions where matter and energy interacted in ways no longer possible today, under densities and temperatures that existed only shortly after the universe began expanding. In this environment, physics operates at extremes, where small differences can produce massive effects, and where energy fields that no longer dominate today may have shaped the behavior of space itself. This leads scientists to ask whether the patterns Webb is detecting could carry indirect traces of the process that drove inflation, the rapid expansion thought to have occurred at the very beginning. Inflation is believed to have been powered by a high-energy field that filled space uniformly, driving expansion while imprinting tiny variations that later grew into structure. And although inflation itself happened far earlier than any direct observation can reach, its effects should still be visible in how matter and energy were distributed afterward. If Webb is seeing unusually early and intense structure formation, it could imply that the initial conditions left by inflation were more energetic or uneven than previously assumed, allowing matter to collapse faster and ignite sooner. The presence of massive stars or compact energy sources so early would suggest that density fluctuations were strong enough to overcome opposing forces almost immediately, a scenario that points back toward the nature of inflation itself. Some of the observed gas clouds show sharp boundaries and directional features, as if shaped by strong radiation or pressure gradients, possibly relics of early energy flows that trace back to inflation-driven variations. These shapes are not smooth or random, but show signs of alignment and coherence across large scales, hinting that the early universe may have retained memory of its initial expansion patterns longer than expected. If inflation produced fluctuations with slightly different properties than standard models predict, those differences would influence how gas collected, how stars formed, and how energy moved through space, effects that James Webb is now positioned to detect. The idea is not that Webb is seeing inflation directly, but that it may be observing the consequences of inflation preserved in the earliest visible structures, written into the arrangement and behavior of primordial matter. Every unusual brightness pattern, every unexpected spectral feature, every early concentration of energy becomes a data point in this investigation, helping scientists test whether existing inflation models fully explain what is now being observed. Some models predict a smoother early universe, others allow for more dramatic early structure, and Webb's data appears to favour scenarios where early energy differences played a stronger role, though interpretation remains careful and cautious. The possible detection of population 3 stars adds another layer to this picture because their formation requires very specific conditions: rapid collapse, intense cooling through limited channels, and strong gravitational influence, all of which depend on the early energy landscape. If these stars formed earlier and more frequently than expected, it suggests the universe moved quickly from expansion to structure, compressing matter efficiently in a way that reflects its earlier state. Exotic energy signatures, primordial gas behavior, and early star formation all point toward a universe that was not gently settling after inflation, but actively reshaping itself at high speed, driven by forces set in motion at the very beginning. James Webb does not tell this story through a single image or a single object, but through patterns repeated across independent observations, patterns that suggest the early universe was far more dynamic than previously imagined. Each new dataset adds detail, revealing interactions between gas, radiation, and gravity that trace back toward the conditions that existed just after inflation ended. The telescope's role is not to guess, but to measure, capturing light that carries information from an era when the universe was still finding its shape and when the energy released at the beginning was still echoing through space. If inflation left behind a specific energy fingerprint, it would influence everything that came after. And James Webb may be uncovering that fingerprint indirectly through the way primordial matter behaves under extreme early conditions. The question of whether this hints at what sparked inflation remains open, but the observation suggests that the universe's earliest visible structures are closely tied to the energy processes that dominated its first moments. By observing primordial gas clouds before they fully become galaxies, by catching the glow of the first stars as they ignite, and by detecting energy signatures that defy simple explanation, James Webb is pushing observation closer to the edge of cosmic history than ever before. Could this redefine the timeline of the universe's first moments? For decades, the timeline of the universe's earliest moments has been drawn like a clean sequence. Inflation first, then cooling, then particles, then atoms, then darkness, then the first stars much later. A slow and orderly progression shaped by equations and simulations built on limited observation. But James Webb's data presses directly against that neat timeline, forcing scientists to reconsider how fast those early steps may have unfolded. Inflation theory says the universe expanded extremely fast at the very beginning, stretching space itself in a fraction of a second, smoothing out chaos and planting tiny differences in density that would later grow into everything we see. And for a long time, those differences were thought to remain small and quiet for hundreds of millions of years before turning into visible structure. What Webb is showing suggests that those early density differences may have turned into real objects far sooner than expected, meaning the universe may have moved from expansion to structure faster than the standard timeline allows. If massive gas clouds collapsed quickly and formed stars earlier, then the period once thought of as a long dark age may have been much shorter or very different in character, filled not with silence, but with early bursts of light and energy. Inflation theory itself does not forbid this because it predicts variations in density, but it leaves open how efficiently those variations grow once inflation ends, and Webb's observation suggests that growth may have been far more aggressive. This raises questions about the inflation field, the energy source thought to drive that rapid expansion, because the properties of that field determine how strong the initial density differences were and how they were distributed across space. If inflation left behind stronger or more sharply defined differences than assumed, then matter would have had an easier time clumping early, forming structures at a speed that now appears closer to what Webb is seeing. This does not rewrite inflation theory, but it may narrow the range of inflation models that fit reality, favoring those that allow early structure to rise quickly from the initial condition. Dark matter plays a central role in this story because it provides the gravitational backbone that allows ordinary matter to collapse, and dark matter does not interact with light, meaning it began shaping structure long before stars ever formed. Standard timelines assume dark matter clumped first, slowly pulling in gas over long periods. but Webb's data hints that this process may have been more efficient, with dark matter halos forming early and deep enough to trap gas almost immediately. If dark matter halos grew faster, then gas clouds would cool and collapse sooner, lighting up the universe earlier than predicted, and this would shift the entire timeline of early cosmic events forward. This does not require new dark matter particles or exotic physics, but it does require revisiting how dark matter behaved under early conditions, when temperatures were high and expansion rates were changing rapidly. The relationship between inflation and dark matter becomes more important here because inflation sets the stage, while dark matter carries out the work of building structure, and Webb's observation suggests that this handoff may have been more direct and faster than models assume. Dark energy enters the picture differently because it does not dominate the early universe the way it does today, but its presence still affects how scientists interpret expansion over time. By measuring early structures and comparing them to later ones, scientists refine how expansion slowed, sped up, and changed character, and Webb's early data helps anchor the early end of that expansion history more tightly. If early structures formed sooner, then the balance between matter and expansion pressure must be examined carefully, because structure formation depends on gravity overcoming expansion at the right moments. Webb's observations imply that gravity gained the upper hand locally very early, allowing cosmic structures to emerge even while the universe as a whole continued expanding rapidly. This early success of gravity affects how cosmic structures scale up, from small gas clouds to galaxies to clusters, and it reshapes the growth curve used in cosmological models. Cosmic structures are not just collections of stars. They include filaments of gas, networks of dark matter, and vast empty regions, all shaped by initial conditions. And Webb's data suggests these patterns began forming earlier than expected. If filaments and dense regions appeared sooner, then the cosmic web may have assembled rapidly, giving early galaxies access to streams of gas that fueled intense star formation. This could explain why some early objects appear unexpectedly bright and massive, because they were not isolated but already connected to larger structures feeding them material. Inflation theory predicts a nearly uniform universe with slight ripples, but it does not dictate how quickly those ripples turn into visible features, and Webb's findings suggest that the transition from ripple to structure happened at a faster pace. This challenges the idea of a long delay between the universe becoming transparent and the first lights turning on, replacing it with a picture where the universe wasted little time getting active. Dark matter simulations often rely on assumptions about cooling, feedback, and collapse that are tuned to match later observation, and Webb now provides early checkpoints that those simulations must hit as well. If simulations fail to reproduce Webb's early structures, then something in the assumed physics must change, whether in how gas cools, how radiation escapes, or how energy flows through early systems. This process of adjustment does not weaken cosmology, it sharpens it, forcing models to stay grounded in observation rather than convenience. The timeline of the universe's first moments is not measured in seconds alone, but in transition from inflation to particle formation to light release to structure. And Webb's data suggests some of those transitions may overlap more than previously thought. Rather than neat stages separated by long gap, the early universe may have experienced rapid overlap, with structure beginning while other processes were still underway. This overlapping timeline fits with a universe that was highly energetic and efficient, converting initial conditions into complexity quickly. If the first stars formed earlier, then chemical enrichment began sooner, influencing later generations of stars and galaxies. And this ripple effect reshapes the entire history that follows. Dark matter halos forming early would also affect black hole formation, galaxy mergers, and large-scale structure, compressing the timeline of many events previously spread out over hundreds of millions of years. Inflation remains the opening act, but Webb's observation suggests that what followed may have been faster, brighter, and more crowded than the calm early universe once imagined. The universe's first moments are not directly visible, but their influence is written into the timing and nature of everything that came after, and Webb's ability to see closer to that beginning makes those influences clearer. By tightening the early timeline, Webb forces scientists to align inflation theory, dark matter behavior, and cosmic structure formation into a more compact and energetic sequence. Each adjustment brings the story closer to what the universe itself recorded in light and matter, not as a simple timeline on paper, but as a dynamic process unfolding at extreme speed. The early universe, as revealed by Webb, appears less like a slow awakening and more like a rapid ignition, where the seeds planted by inflation took root almost immediately, shaping space with gravity, matter, and energy in ways that continue to define the cosmos today. Challenges to existing models. When James Webb started returning deep observations from the early universe, the first reaction was not celebration, but confusion, because many of the things appearing in the data were not supposed to be there so early, and this immediately put pressure on models that had been trusted for years. Most accepted models describe the early universe as slow to organize, with matter taking time to cool, gather, and form the first stars and galaxies. Yet Webb shows bright, structured objects appearing far earlier than those models allow, which means the math that predicts when structure should appear no longer lines up cleanly with what is being observed. One of the first challenges comes from galaxy growth rates, because models assume limits on how fast gas can fall into dark matter halos, turn into stars, and produce light. And Webb's observations suggests that this process may happen much faster under early conditions than previously assumed. Many models rely on feedback effects to slow things down, where early stars heat surrounding gas and prevent further collapse. But Webb shows signs of continued rapid star formation, which suggests that feedback may have been weaker, delayed, or operating differently in the early universe. This forces scientists to revisit how energy from early stars interacts with primordial gas, because if gas was able to keep collapsing despite radiation, then something about cooling, density, or structure must be missing from current simulation. Another challenge appears in the brightness of early objects, because some galaxies detected by Webb shine far more intensely than models predict for their age. And this brightness implies either very efficient star formation or additional energy sources that are not fully accounted for. If stars formed more efficiently, then assumptions about gas temperature, fragmentation, and collapse must change. And if additional energy sources exist, then models need to include those processes explicitly rather than treating them as rare or negligible. Dark matter behavior also comes under pressure because accepted models assume a certain pace of halo formation, yet Webb's observations imply deep gravitational wells forming earlier, capable of trapping gas and fueling star formation almost immediately. This raises questions about whether dark matter clumped faster under early conditions, or whether its interaction with normal matter was more effective than assumed during the universe's first stages. Even without changing the nature of dark matter itself, models may need to adjust how dark matter halos grow and merge at high redshift, because Webb suggests that the early universe may have been far more crowded with dense regions than expected. Another area under strain is the predicted timeline of reionization, the period when radiation from early stars changed the state of hydrogen across space, because Webb's data hints that powerful radiation sources were active earlier, pushing this process forward. Models that once placed reionization later now struggle to explain why signs of intense radiation appear so close to the beginning, forcing revisions to the assumed number, size, and power of early stars. The structure of early galaxies also challenges expectations, because many appear more organized than models predict, showing signs of disks or concentrated cores at times when turbulence should dominate. This suggests that gravity may have shaped matter into stable forms faster, or that early gas behaved in a more orderly way under extreme conditions than simulations suggest. Simulations often smooth over small-scale effects to make calculations manageable, but Webb's data shows that small-scale processes mattered greatly early on, meaning those shortcuts may no longer be acceptable. Another issue arises from chemical signatures, because models predict very simple compositions early, yet Webb observations sometimes hint at more complex processes happening sooner, which forces scientists to rethink how quickly elements spread and mix. This does not mean heavy elements appeared instantly, but it suggests that early stars may have formed, lived, and died quickly enough to influence their surroundings earlier than expected. Energy transport within early systems becomes another weak point because models assume certain limits on how energy moves through gas and dust. Yet Webb's observations show regions that remain dense and active despite intense radiation. This means models must revisit assumptions about opacity, gas flow, and cooling channels, especially under conditions with no dust or metals. Accepted theories also assume a relatively smooth transition from early chaos to later structure, but Webb shows signs of early complexity that suggest a more uneven path, with bursts of activity followed by rapid organization. This uneven growth challenges models built around average behavior, because Webb is revealing extremes that matter, not just typical cases. Another tension appears in the number counts of early galaxies, because Webb finds more objects at high redshift than predicted, which means models may underestimate how common early structure really was. If early galaxies were more numerous, then matter distribution and collapse efficiency must be revisited, affecting everything from star formation rates to radiation output. Some models depend heavily on assumptions tuned to match Hubble-era observations, but Webb pushes far beyond that range, exposing weaknesses that were hidden simply because no data existed there before. This forces a reset in how models are calibrated, shifting from fitting later observations backward to matching early observations directly. Even inflation-linked predictions feel indirect pressure because the speed and scale of early structure formation reflect the initial conditions left behind at the very beginning. If those conditions led to faster collapse than expected, then some inflation models may fit better than others, narrowing the range of acceptable early universe scenarios. The challenge is not that Webb disproves accepted theories, but that it exposes their limits, showing where assumptions were made for lack of data rather than strong evidence. Each unexpected observation forces modelers to ask whether the issue lies in physics, initial conditions, or simplifications built into simulations. This process is uncomfortable but necessary, because models only remain useful when they reflect reality rather than habit. James Webb acts like a stress test, pushing theories into extreme conditions they were never fully tested against before. When models fail to reproduce what Webb sees, they must either be revised or replaced, not because they were wrong in principle, but because the universe turned out to be more active and efficient early on than expected. The pressure builds not from one observation, but from many, repeating patterns that point in the same direction: faster growth, earlier light, stronger gravity effects. This forces collaboration between observers and theorists, because data alone does not explain itself, and theory alone no longer predicts accurately without adjustment. As revisions take place, some ideas will survive with changes, others will fade, and new approaches will emerge that better match what Webb reveals. The challenge now is to rebuild models that can explain both the smooth early universe seen in background radiation and the intense early activity seen by Webb, without contradiction. That task reshapes modern cosmology, not through dramatic announcements, but through careful correction driven by evidence that cannot be ignored. Possible scenarios. Imagine the universe before anything had shape, before light had a path to travel, before time had a rhythm, a state where space itself was quiet but not empty. Because even in that silence, physics says there was motion at the smallest possible scale. One possible scenario begins with quantum fluctuations, not as a dramatic explosion, but as tiny, restless changes in energy that happen naturally according to quantum physics, even when nothing else seems to exist. In quantum theory, empty space is never truly empty, because energy fields can flicker, rise and fall for extremely short moments, creating brief pockets of energy that normally vanish almost instantly. In the earliest possible state of the universe, before expansion took over, these fluctuations may not have been confined the way they are today, because space itself was different, more compressed, more unstable, and far more sensitive to tiny changes. If one of these fluctuations crossed a critical threshold, it could have triggered rapid expansion, not because something exploded outward, but because space itself began stretching faster than anything inside it could resist. This scenario does not require a spark or an external push, only the natural rules of quantum physics acting under extreme conditions, rules that still operate today, but usually stay hidden at scales too small to notice. James Webb does not see quantum fluctuations directly, but it sees the results that may trace back to them, because the way matter spread out, clumped and cooled carries fingerprints of the earliest energy patterns. Some of the structures Webb observes appear smoother or more uniform than expected, while others show sharp contrasts, which could reflect how early fluctuations were stretched across space during rapid expansion. These patterns matter because inflation theory predicts that quantum fluctuations were stretched to cosmic size, becoming the seeds of galaxies, clusters, and vast empty regions. If Webb is detecting structures that formed unusually fast or in unexpected arrangements, it may be seeing the amplified results of those earliest fluctuations playing out across billions of years. Another scenario focuses on early universe anomalies, features that do not fit neatly into standard predictions, such as galaxies appearing too massive, too bright, or too organized too early. These anomalies may point to uneven energy distribution in the early universe, where some regions received slightly more energy during inflation, allowing matter to gather faster once expansion slowed. James Webb's deep field observations show variations in brightness and density that challenge the idea of a uniform early universe, suggesting that conditions were not the same everywhere. If early space was shaped by uneven energy fields, then those differences would still be visible today, stretched across immense distances and preserved in how matter arranged itself. Some Webb observations hint at sharp transitions in structure, where regions of space appear more developed than neighbouring areas at the same cosmic age. This could reflect early anomalies in expansion speed, energy density, or field strength, which later translated into differences in how quickly stars and galaxies formed. These are not random differences because they follow patterns that can be mapped, measured, and compared with predictions from early universe physics. Another scenario considers whether Webb is seeing indirect signs of early energy events, moments when energy density spiked locally, pushing matter into rapid collapse or intense radiation output. These would not be explosions in space, but changes in space itself, brief phases where energy fields shifted and reshaped how expansion unfolded. Such events could leave behind regions that appear older or more evolved than they should be, because they started forming structure earlier than surrounding space. James Webb detects some galaxies that appear surprisingly mature, with dense star populations and strong radiation signatures, even though they exist at times when the universe was expected to be simpler. One explanation is that these regions experienced early energy boosts that accelerated star formation. These boosts could come from field interactions predicted by some inflation models, where multiple energy fields interact instead of a single smooth one. If inflation involved more than one field, then interactions between them could create localized effects, changing how space expanded in certain areas. Webb cannot see these fields directly, but it can see their aftermath because matter follows the shape of space, and space follows the rules set during the earliest moments. Another possibility is that Webb is seeing traces of early high-energy transitions, moments when the universe shifted from one energy state to another as it cooled. Physics predicts that as the universe expanded and cooled, fundamental forces separated and energy states changed, similar to water freezing into ice. These transitions may not have been perfectly smooth, leaving behind uneven energy distributions that later influence structure formation. If Webb is detecting unexpected clustering or alignment of early galaxies, this could reflect those ancient transitions frozen into cosmic structure. Some observations show early objects forming along filaments earlier than expected, suggesting that large-scale structure emerged quickly. This may point to early energy patterns guiding matter into specific paths, rather than matter spreading evenly and slowly collapsing later. Another scenario explores whether Webb is seeing the edge of inflation's aftermath, not the beginning itself, but the earliest visible consequences of space settling into a calmer expansion. Inflation would have ended extremely fast, but the conditions it left behind would shape everything that followed. If Webb is detecting unusually smooth regions next to highly structured ones, this contrast may reflect how inflation ended unevenly across space. Some models predict that inflation did not stop everywhere at the same time, leading to variations that would still be visible today. These variations would influence how soon gas cooled, how fast stars formed, and how much light early galaxies produced. Webb's ability to detect faint infrared signals allows it to see these early differences more clearly than any telescope before it. Another idea involves vacuum energy changes, where the energy of empty space itself shifted, altering expansion behavior. Vacuum energy today drives accelerated expansion through dark energy, but its strength may have been different early on. If vacuum energy decayed or changed rapidly at the beginning, it could have released energy into space, affecting matter distribution. Webb observations that suggest early intense radiation could be indirect evidence of such changes. This does not mean Webb sees the Big Bang trigger directly, but it may be seeing the consequences of early energy reshaping the universe. Some scenarios also explore whether early black holes form faster than expected, acting as energy engines that shaped early structure. If massive black holes form from direct collapse of gas rather than from stars, they could appear very early and influence surrounding matter. Webb has detected candidates for extremely early massive objects, which raises questions about how such dense concentrations formed so quickly. These objects could represent regions where energy and matter concentrated unusually early, possibly linked to initial conditions. Another scenario considers whether known physics is incomplete at these extremes, and Webb is revealing behavior that requires refinement rather than replacement of theory. In this case, quantum fluctuations, inflation, and known forces still apply, but their interaction under early conditions produces effects that models simplified or ignored. Webb's role becomes that of a witness, not to the trigger itself, but to the ripples left behind by that trigger. Each unusual structure, brightness spike, or early formation event acts like a clue, pointing backward toward conditions that no longer exist, but left their mark. The key idea across all scenarios is that Webb is not showing a single clear cause, but multiple consistent hints that early energy behavior was more complex than expected. These hints do not rewrite physics on their own, but they force closer examination of how the universe moved from near uniform energy to structured space. What Webb sees today is ancient light stretched across time, carrying information about density, motion, and energy from moments close to the beginning. If those signals continue to show patterns that align with quantum-driven inflation scenarios, then confidence grows that the universe began not with a classic event, but with natural physical processes operating at extreme scales. If anomalies persist and sharpen, they may point to early energy events that added complexity to the universe's birth story. James Webb does not answer the question of what triggered everything, but it narrows the field of possibilities by revealing what the universe looked like immediately after that trigger took effect. Each observation removes guesswork and replaces it with measurable structure, light, and motion. What remains is a universe that remembers its earliest moments not in words or equations, but in the way it grew, clumped, and lit up the dark. How JWST does it: observation techniques. Imagine light leaving a young galaxy when the universe was still new, at a time when space was smaller, hotter, and packed tight. That light begins its journey bright and energetic. But the universe does not stay still while the light is traveling. As space expands, the distance between points grows, and light moving through that space gets stretched along with it, not because it slows down, but because the fabric it rides on keeps pulling apart. This stretching changes light's colour, shifting it from short wavelengths like ultraviolet and visible light into longer wavelengths, which we call infrared. A galaxy that once shone in sharp blue or white light ends up arriving at us as a faint infrared glow, carrying the same information but transformed by time and expansion. This effect is called redshift because as wavelengths stretch, light moves toward the red end of the spectrum and then beyond it into infrared, where human eyes can no longer see. The farther back in time the light comes from, the more the universe has expanded while that light was travelling, and the more stretched it becomes. For the earliest galaxies, the stretching is extreme, pushing their light entirely out of the visible range. This is where James Webb changes everything. Most older telescopes were built to see visible light, the kind our eyes evolved to detect, which works well for nearby stars and galaxies, but fails when light has been stretched too far. Hubble could see some infrared, but its mirror and instruments were not designed to focus deeply on the faintest, longest wavelengths from the earliest times. James Webb was built from the ground up to live in the infrared, not as an extra feature, but as its main purpose. Its giant gold-coated mirror reflects infrared light efficiently, gathering faint signals that would pass straight through other telescopes unnoticed. The mirror's size matters because early universe light is not just stretched, it is also incredibly weak after travelling for billions of years. Every extra bit of collecting area increases the chance of catching those ancient photons. Webb's instruments are cooled to extremely low temperatures because infrared light is closely tied to heat, and any warmth from the telescope itself would drown out the signals it is trying to detect. By chilling the instruments, Webb removes its own glow from the picture, allowing distant light to stand out against the darkness. When infrared light reaches Webb, it is directed into instruments that do more than take pictures. They break the light apart into its component wavelengths, creating spectra that act like fingerprints. Each element absorbs and emits light at specific wavelengths, so by studying these patterns, scientists can tell what a distant object is made of. The amount of redshift seen in these spectral lines tells how much the universe has expanded since the light was emitted. This allows scientists to calculate how far back in time they are looking. The more shifted the lines, the earlier the object. Webb can detect redshifts so extreme that they push the boundary of how close to the beginning we can observe. Optical telescopes struggle here because they rely on light that simply no longer arrives in visible form. It is not that the early universe was dark, but that its light has been stretched beyond what optical eyes can catch. Webb's sensitivity allows it to see objects that are not just distant, but faint beyond anything previously detected. This matters because early galaxies were smaller, less massive, and produced less light than modern ones. To find them, a telescope must detect signals barely above the background noise of space. Webb's detectors are designed to count individual photons, measuring their energy and arrival time with extreme precision. This precision allows scientists to separate real signals from random noise. Another advantage comes from Webb's stable observing environment far from Earth. Orbiting far away, Webb avoids the heat, light, and interference that affect telescopes closer to home. This stability allows long exposures, where the telescope stares at one patch of sky for days, slowly building up an image from countless faint signals. Each hour of observation adds more detail, revealing objects that were invisible at first glance. This technique is how deep field images are made, showing thousands of galaxies packed into a tiny region of sky. Infrared light also passes more easily through dust than visible light. In the early universe, dust from early stars could hide regions from optical telescopes. Webb sees through this dust, revealing structures that were previously concealed. This gives a clearer view of how matter was arranged and how stars formed inside early clouds. Redshift does more than tell distance, it tells motion. The amount of stretching reveals how fast space was expanding when the light was travelling. By measuring redshifts across many objects, scientists can map how expansion behaved at different times. Webb's data allows these measurements at earlier times than ever before. This helps refine models of how quickly the universe expanded and how that expansion influenced structure formation. Infrared observation also reveals cooler objects. Early stars and gas clouds emit light at wavelengths that shift into infrared as they cool and expand. Webb can detect these signals, providing insight into the temperatures and densities of early matter. Optical telescopes miss much of this information because they are blind to longer wavelengths. Another key technique involves comparing multiple infrared filters. Webb takes images through different filters, each tuned to a specific range of wavelengths. By comparing brightness across filters, scientists can estimate redshift even before taking detailed spectra. This allows rapid identification of candidate early objects. Once candidates are found, Webb uses spectroscopy to confirm their distances and properties. This layered approach speeds up discovery while maintaining accuracy. Webb's resolution also plays a role. Even though infrared light has longer wavelengths, Webb's large mirror allows it to resolve fine details. This means early galaxies are not just detected as smudges, but often show structure. Seeing structure helps confirm that these are real galaxies, not noise or closer objects mistaken for distant ones. Time plays a role as well. Webb can observe the same region repeatedly, tracking changes and refining measurements. This repeated observation reduces uncertainty and strengthens confidence in results. All of these techniques work together. Infrared sensitivity captures stretched light. Cooling removes interference. Large mirrors gather faint signals. Spectroscopy reveals composition and distance. Long exposures pull objects out of darkness. The result is a telescope capable of seeing the universe when it was less than 1 billion years old. James Webb does not look for the beginning by searching for an explosion. It looks for the earliest light that survived expansion and still carries information about its origin. Every infrared photon Webb collects is a message sent billions of years ago. By reading those messages, scientists reconstruct how the universe changed as it grew. This method does not rely on guesswork. It relies on light behaving the same way across time, stretching as space stretches. Webb's power comes from following that rule all the way back to the edge of what can be observed. What it reveals is not just distant objects, but the process of cosmic history written in light that has travelled longer than anything else we can see. Spectroscopy and cosmic fingerprints. When light reaches James Webb, it is guided into instruments that separate it by wavelength, spreading it out into a long band where each tiny section corresponds to a specific energy level. This spread out light is called a spectrum, and it looks like a barcode made of bright lines, dark gaps, and subtle shifts in position. Every atom and molecule interacts with light in its own exact way. Because electrons inside atoms can only move between specific energy levels, when an atom absorbs energy, it removes light at very precise wavelengths, creating dark lines in the spectrum. When it releases energy, it adds light at those same exact wavelengths, creating bright lines. These patterns never change, no matter where the atom exists in the universe, which means hydrogen in the early universe leaves the same spectral marks as hydrogen measured in a lab on Earth. This consistency allows scientists to identify elements across billions of years and unimaginable distances. James Webb collects these spectra from faint, distant objects and compares the patterns to known atomic fingerprints. If hydrogen is present, its signature appears. If helium exists, its lines show up in predictable places. If heavier elements like carbon, oxygen, or nitrogen are detected, their presence is unmistakable because their spectral patterns are complex and specific. This is how scientists determine what early galaxies and gas clouds are made of without ever touching them. Temperature information is also encoded in light because hotter objects emit light differently than cooler ones. As temperature increases, atoms become more energetic and produce stronger or broader spectral lines. Hot gas shows wide, intense features, while cooler gas produces narrower and weaker ones. By measuring the width and strength of these lines, scientists calculate the temperature of distant matter. This is crucial for understanding early stars because their temperatures reveal how massive and energetic they were. James Webb detects infrared light that comes from gas heated by early stars, allowing scientists to measure conditions inside galaxies that existed when the universe was still very young. Velocity information is hidden in the position of spectral lines. When an object moves toward us, its light shifts slightly toward shorter wavelengths. When it moves away, the light shifts toward longer wavelengths. This shift is called the Doppler effect, and it allows scientists to measure motion across space. With Webb's precision, even tiny shifts can be detected, revealing how fast gas is moving inside early galaxies. These measurements show whether gas is falling inward, being pushed outward by radiation, or rotating around a central region. Velocity data reveals internal structure, showing whether early galaxies were chaotic clouds or already forming ordered systems. Spectroscopy also allows scientists to measure how fast entire galaxies are moving away due to cosmic expansion. By comparing known spectral lines to their observed positions, the amount of redshift can be measured precisely. This redshift directly tells how much the universe has expanded since the light was emitted. That expansion value translates into distance and time, placing the object on the cosmic timeline. James Webb's instruments can measure redshifts so extreme that they reach into eras never explored before. Spectral fingerprints also reveal density. In dense environments, atoms collide frequently, changing how they absorb and emit light. This alters the shape and intensity of spectral lines. By analysing these changes, scientists estimate how tightly packed gas was in early regions. Density measurements help explain how quickly stars could form and how intense early star formation may have been. Chemical fingerprints tell another story, one tied to cosmic history. The earliest universe contained almost no heavy elements. Hydrogen and helium dominated, with trace amounts of lithium. Heavier elements form inside stars and are spread when stars die. If Webb detects heavier elements in very early galaxies, it means stars formed, lived, and influenced their surroundings quickly. Spectroscopy allows scientists to measure not just presence, but relative abundance. This shows how chemically evolved an object is, even at early times. James Webb's infrared sensitivity is critical here, because many key spectral lines from early objects are shifted out of the visible range. Lines that once appeared in ultraviolet light now fall deep into infrared wavelengths. Older telescopes could not see these lines clearly or at all. Webb captures them with clarity, revealing details that were previously invisible. Another layer comes from molecular spectroscopy. Molecules like molecular hydrogen leave faint but distinctive marks in infrared light. Detecting these molecules shows where gas has cooled enough to begin forming stars. Webb can identify these signatures, mapping regions where star formation was beginning or already underway. This helps scientists understand how quickly the universe transitioned from simple gas to complex structure. Spectroscopy also reveals energy sources. Different processes produce different spectral shapes. Light from stars has one pattern. Light from gas heated by intense radiation has another. Light influenced by black holes shows additional features. By comparing observed spectra to known models, scientists determine what powers early objects. This matters because early energy sources shape how galaxies grow and how surrounding space changes. Time information is layered into spectroscopy as well. By observing the same object over long periods, scientists refine measurements and reduce uncertainty. Repeated spectra confirm whether features are real or artifacts. This builds confidence in results drawn from extremely faint signals. James Webb's stable environment allows these long, careful observations. Spectroscopy also exposes interactions between light and matter along the path to Earth. As light travels, it passes through clouds of gas that absorb specific wavelengths. These absorption features appear in spectra as additional lines. By studying them, scientists map gas between galaxies, revealing how matter was distributed across space. This intergalactic gas holds clues about early structure formation and energy flow. Each spectrum collected by Webb acts like a record of conditions across time. It carries information about composition, motion, heat, density, and history. No single line tells the full story. It is the combination of many lines, shifts, and shapes that builds a complete picture. This process is slow, careful, and data-driven. Spectroscopy does not rely on interpretation alone. It relies on physical rules that have been tested repeatedly in laboratories. That reliability is why spectroscopy is trusted to probe the earliest epochs. James Webb extends this method farther than ever before, pushing spectral analysis into times when the universe was only a small fraction of its current age. The cosmic fingerprints it collects are not guesses or artistic impressions. They are measurable signals governed by known physics. Each detection tightens constraints on models and removes uncertainty. Through spectroscopy, Webb turns faint infrared light into detailed physical information. That information reveals how matter behaved, how energy flowed, and how motion unfolded near the beginning. The universe leaves its history written in light, and spectroscopy is the tool that reads that writing with precision, depth, and clarity across the largest distances ever explored. Multiple instrument collaboration. James Webb's power comes not from a single instrument, but from the way its four main instruments, NIRCAM, NIRSPEC, MIRI, and FGS/NIRISS, work together, each capturing different aspects of the same object, and combining their data produces insights far beyond what any one instrument could provide on its own. NIRCam, the near-infrared camera, is Webb's primary imaging tool, designed to capture extraordinarily detailed pictures of faint, distant galaxies and stars, detecting light stretched into the infrared by billions of years of cosmic expansion. It allows scientists to see the shape, size, and structure of galaxies at high redshift, revealing whether they are compact, diffuse, or already forming disks. And it is sensitive enough to detect faint star clusters embedded in gas clouds, providing a first map of where stars and galaxies are forming. NIRSpec, the near-infrared spectrograph, complements NIRCam by taking the light collected and splitting it into spectra, revealing the fingerprints of elements, temperatures, densities, and velocities within those galaxies. While NIRCam shows the universe visually, NIRSpec tells the chemical and physical story hidden in the light, indicating which elements are present, whether hydrogen, helium, or heavier metals exist, and how stars and gas are moving relative to each other. By combining imaging from NIRCAM and spectroscopy from NIRSPEC, scientists can link structure to physical properties, mapping regions of star formation, observing how gas flows in and out of galaxies, and identifying which areas are actively forming stars while others remain dormant. MIRI, the mid-infrared instrument, extends this capability into longer wavelengths, detecting cooler objects that NIRCam and NIRSpec cannot see, including dust-enshrouded regions and early stellar nurseries. It reveals areas where dust absorbs starlight and re-emits it in the mid-infrared, which is essential for understanding the full energy output of early galaxies and the role dust plays in shaping star formation and galaxy evolution. MIRI's ability to detect these faint, cool emissions allows scientists to identify structures that would otherwise remain invisible, such as primordial gas clouds where the first population 3 stars might be forming, or regions of early black hole activity hidden by surrounding matter. By combining MIRI data with NIRCam's imaging and NER-SPEC's spectroscopy, researchers get a more complete picture of both the hot, energetic regions and the cooler, dust-covered areas, connecting the early universe's visible and hidden processes in a single dataset. FGS/NIRISS, the Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph, contributes to this collaboration by precisely guiding the telescope while also providing additional imaging and spectral information. Its fine-pointing capability ensures that NIRCam, NIRSPEC, and MIRI can focus accurately on distant targets over long observation periods, maintaining stability that allows extremely faint light to be collected without blur or distortion. NIRIS also performs slitless spectroscopy, capturing spectra of multiple objects in the field of view simultaneously, which is invaluable for surveys of dense galaxy clusters and for identifying early galaxies in crowded regions. The integration of all 4 instruments allows scientists to correlate data across multiple dimensions. For example, a distant galaxy may first be imaged in detail with NIRCam, showing a compact, bright core with faint surrounding structures. NIR-SPEC can then analyze the light from that galaxy to determine redshift, chemical composition, and internal gas motions, confirming its age and revealing which regions are actively forming stars. MIRI can detect infrared emission from surrounding dust, revealing cooler regions that contain gas not yet forming stars or obscured early black hole activity. NIRIS contributes additional spectral data and ensures that the telescope's pointing remains precise throughout long exposures. This combination allows each discovery to be verified and analysed from multiple angles simultaneously, reducing uncertainty and uncovering details that would remain hidden if only one instrument were used. A galaxy that appears faint in NIRCam images may be brighter in MIRI's mid-infrared, revealing hidden star formation, while NIRSPEC spectra confirm the galaxy's chemical maturity, and NIRISS identifies nearby companion objects or overlapping sources that could otherwise confuse the analysis. By layering these datasets, scientists can reconstruct the physical, chemical, and dynamical history of objects as they existed billions of years ago. Multiple instrument collaboration also enables the detection of rare or extreme phenomena. For example, unusually bright galaxies or objects with unexpected chemical compositions can be cross-checked across all instruments, confirming that these signals are real and not artifacts. The combined data reveal correlations, such as the relationship between star formation rate, dust content, and gas motion, providing a complete picture of the processes shaping the early universe. Webb's ability to integrate NIRCam, NIRSPEC, MIRI, and NIRISS data transforms raw infrared photons into a detailed narrative of galaxy formation, early stellar evolution, and the distribution of matter in the first billion years. In practical terms, the collaboration means that a single observation session can produce imaging, spectra, and thermal information simultaneously, eliminating the need for separate follow-up observations that would take months or years with older telescopes. This efficiency allows scientists to explore larger regions of the early universe and to identify anomalies or structures that would have been impossible to detect otherwise, such as massive early galaxies, dense star clusters, or unexpected bursts of star formation. Each instrument fills a gap left by the others, and together they provide a multi-layered, multi-dimensional dataset that captures the complexity of the universe at its earlier stages. The synergy between ENIACAM, ENIASPEC, MIRI and NEARIS also enables discoveries that challenge existing models. Bright, massive galaxies detected in NIACAM images can be chemically characterized with NEASPEC, revealing unexpectedly high metal content that pushes back timelines for star formation. MIRI observations may detect warm dust around these galaxies, indicating that star formation and supernova activity happened even earlier than previously thought, while NEARIS slitless spectra can reveal multiple neighbouring galaxies forming simultaneously in the same region. These overlapping insights make it possible to trace how structure, chemistry and energy interact across space and time, building a complete story from the earliest observable moments of cosmic history. By combining data from multiple instruments, James Webb turns each observation into a multi-dimensional exploration, allowing scientists to link morphology, composition, motion, and temperature in a single discovery. This collaborative approach transforms isolated photons into a rich map of the early universe, revealing the interplay of matter, energy, and structure that occurred when the cosmos was still young. And it is this layered, instrument-integrated methodology that enables discoveries of galaxies, star clusters, and cosmic phenomena that challenge theories, redefine timelines, and expand our understanding of the universe's origins. What it means for future astronomy. James Webb has opened a door to a universe no one expected to see in such detail, and the implications stretch across every field of astronomy, from the tiniest gas clouds to the largest cosmic structures. Planned follow-up observations are already in motion, aiming to confirm whether the hints Webb has detected could lead to understanding what triggered the Big Bang, or whether they are pointing toward phenomena that expand our knowledge of cosmic evolution in unexpected ways. Teams around the world are preparing new campaigns to look deeper, longer, and across different wavelengths, targeting regions where the earliest galaxies appear, where primordial gas clouds may still linger, and where exotic energy signatures suggest something extraordinary occurred in the universe's first few 100 million years. Each observation session is meticulously designed, using Webb's multiple instruments together to extract as much information as possible, combining imaging, spectroscopy, and mid-infrared data to construct a complete picture of objects that existed when the universe was a fraction of its current age. Surveys of early galaxies are now a priority, with programs that map large regions of space at unprecedented depth. These surveys aim not only to count galaxies, but to understand how they formed, how quickly they built stars, and how their chemical composition changed over time. Webb can detect galaxies that formed astonishingly early, some with more structure than models predicted, and scientists want to measure how common these galaxies are, how massive they became, and how their light interacts with surrounding gas and dust. These observations can reveal the rate of star formation, the efficiency of early galaxy growth, and whether massive black holes existed earlier than expected. Each new galaxy detected adds a piece to the puzzle of how the universe transitioned from a smooth field of gas into a complex web of stars, galaxies, and clusters. Primordial phenomena, such as the first generation of stars, known as Population 3, are also high on the agenda. These stars, thought to contain only hydrogen and helium, may have left imprints in the chemical composition of early galaxies, detectable through Webb's spectroscopy. Scientists plan to identify candidate regions where these stars may have existed, mapping spectral lines that indicate pristine gas untouched by heavier elements. If such stars can be observed or indirectly inferred, it will provide insight into how the first sources of light shaped rhionization, the period when the universe transitioned from opaque to transparent. Webb's sensitivity allows detection of these subtle features, offering the possibility to witness the earliest star formation and the first cosmic explosions that enriched surrounding space. Follow-up observations are also designed to explore unusual energy signatures detected in early surveys. Some regions show radiation patterns that suggest highly energetic events, possibly related to rapid star formation, early black holes, or fluctuations in primordial energy fields. Scientists plan extended spectroscopy campaigns, observing the same regions repeatedly to confirm the presence, strength, and structure of these signals. Understanding these events may reveal processes that contributed to cosmic inflation, the rapid expansion that shaped the large-scale structure of the universe. If these energy patterns correspond to regions of accelerated star or galaxy formation, it could indicate that the early universe was far more dynamic than previously imagined. James Webb is also expected to perform targeted deep-field observations, focusing on tiny patches of sky for weeks at a time, collecting faint light from the most distant and oldest objects. These ultra-deep surveys aim to find galaxies at redshifts higher than any seen before, pushing the limits of how far back we can observe. Long exposures increase the chance of detecting the faint glow of the first galaxies and any associated structures, allowing astronomers to study the distribution, mass, and chemical composition of these objects. The deep field strategy will not only expand the catalogue of early galaxies, but also help refine models of how cosmic structures emerge from the initial uniformity of space. Next-generation surveys plan to combine data from multiple JWST programs to build large-scale maps of the early universe. By stitching together observations from different regions and wavelengths, scientists can track patterns in galaxy formation, examine clustering, and identify voids where matter is sparse. These maps are essential for testing predictions of cosmological models, including the behavior of dark matter and dark energy in shaping the cosmos. Webb's infrared sensitivity allows it to see through dust and reveal hidden structures, providing a clearer view of the distribution of matter during the first billion years of cosmic history. Observing primordial gas clouds is another crucial step. These clouds are the reservoirs from which the first stars formed, and their composition and density carry information about the processes that governed early star formation. Webb's spectroscopy can determine whether these clouds contain only hydrogen and helium, or if heavier elements are already present, which would indicate that stars formed and enriched the universe faster than expected. Detecting these clouds in emission or absorption and correlating their properties with nearby galaxies allows scientists to reconstruct the timeline of cosmic evolution and test theories about how quickly the universe transitioned from simplicity to complexity. Repeated observations over time will also play a key role. Certain early objects may vary in brightness, and long-term monitoring allows astronomers to track changes that reveal underlying physical processes. Variable light can indicate star formation bursts, early supernovae, or the growth of nascent black holes. Observing these variations helps create a dynamic picture of the early universe, showing not just where galaxies exist, but how active they were and how energy flowed across cosmic structures. JWST's ability to combine imaging and spectroscopy with mid-infrared sensitivity enables unprecedented multi-layered studies. Observing the same object across NIRCam, NIRSpec, MIRI, and NIRISS instruments provides detailed information on morphology, chemistry, temperature, and dust content all at once. This multi-instrument approach allows astronomers to detect hidden star-forming regions, trace energy flows, measure chemical evolution, and determine internal motions within early galaxies. Such data makes it possible to test whether the conditions Webb observes are consistent with predictions from inflation theory, and whether they offer hints of what may have triggered the rapid expansion of space in the universe's first moments. Upcoming programs also plan to focus on extreme or unusual objects, such as massive early galaxies, dense star clusters, or galaxies with chemical compositions that defy expectations. These objects may provide clues about the speed of early star formation, the efficiency of gas-to-star conversion, and the emergence of the first black holes. By cataloguing these anomalies and comparing them across multiple regions of the sky, scientists aim to determine whether they represent rare occurrences or fundamental features of the early universe. Such studies have the potential to challenge existing cosmological models, forcing revisions to the timeline of structure formation and the processes that shape the universe. The combination of deep surveys, targeted spectroscopy, repeated observations, and multi-instrument integration allows James Webb to transform the way early cosmic history is studied. The telescope's observations create opportunities to test theories about the first stars, the formation of galaxies, and the distribution of matter. And these programs will refine our understanding of how energy, chemistry, and structure emerged across time. Scientists will compare Webb data to previous surveys from Hubble, Planck, and ground-based observatories, examining consistencies and discrepancies to construct the most accurate timeline yet of the universe's formative years. Every planned follow-up observation builds on discoveries already made, adding detail, precision, and context. Webb's ability to detect faint galaxies, measure chemical abundances, and track motions across billions of light years allows astronomers to explore early cosmic processes with an accuracy never before possible. Surveys will identify patterns in galaxy clustering, variations in star formation rates, and regions where early energy events may have accelerated evolution. The accumulation of these observations will produce a dataset that informs models of cosmic inflation, the formation of the first stars, and the emergence of large-scale structure, while also revealing surprises that challenge expectations and inspire new theoretical developments. JWST's future observations will not be limited to individual galaxies. Mapping the distribution of matter on larger scales allows scientists to investigate cosmic filaments, voids, and the arrangement of early galaxy clusters. Understanding the connections between these structures sheds light on the role of dark matter and dark energy in shaping the cosmos. Webb's multi-instrument capabilities provide detailed imaging and spectra across these regions, making it possible to study both the physical properties of individual galaxies and the larger-scale structure of space at the same time. Special programs will focus on detecting the earliest supernova, explosions of the first massive stars that enrich the universe with heavy elements. Observing these events allows scientists to measure how quickly chemical enrichment occurred and to determine the impact of early supernova on surrounding gas and star formation. Webb can capture the infrared glow from these explosions, even if they are obscured by dust, providing insight into processes that occurred when the universe was less than 1 billion years old. Surveys targeting primordial black holes and high-energy phenomena aim to detect the seeds of supermassive black holes that dominate galaxies today. Spectroscopy and imaging across multiple instruments help trace the growth and influence of these early objects, determining whether they form directly from gas clouds or as remnants of the first massive stars. These studies contribute to understanding how extreme energy events shape the evolution of galaxies, the intergalactic medium, and large-scale cosmic structure. The synergy between surveys, deep-field imaging, and spectroscopy enables scientists to identify correlations that reveal how early galaxies interacted with each other and with their environment. Observing clusters of galaxies forming in the first billion years helps determine how gravity, dark matter, and energy flows influence the assembly of cosmic structures, while repeated observations track changes over time, revealing dynamic processes that shape the evolution of the universe at its earliest stages. JWST's future programs also include searches for unusual spectral signatures that may indicate exotic processes in the early universe, such as unexpected chemical ratios or energy emissions inconsistent with current models. Detecting these features could point to phenomena related to inflation, quantum fluctuations, or other mechanisms that set the initial conditions for cosmic evolution. The telescope's ability to capture these faint signals across multiple wavelengths and instruments makes it possible to identify anomalies with confidence, allowing scientists to explore the limits of current cosmological theory and expand understanding of how the universe came to be. The integration of imaging, spectroscopy, and mid-infrared observations creates datasets that are multidimensional, offering insights into morphology, composition, temperature, velocity, and dust content simultaneously. Each early galaxy or primordial structure becomes a case study in cosmic evolution, with Webb providing detailed evidence of how stars formed, how galaxies grew, and how matter and energy interacted in the universe's formative epochs. These datasets form the foundation for future research, guiding new theoretical models and informing observations with other telescopes across the electromagnetic spectrum. As JWST continues its mission, planned surveys will expand to cover larger areas, identify more rare or extreme objects, and explore regions previously inaccessible due to distance, faintness, or dust obscuration. The combination of repeated observations, high-resolution spectroscopy, and multi-instrument analysis ensures that each discovery builds upon the last, creating a comprehensive map of early cosmic history that charts the emergence of stars, galaxies, and energy patterns that shape the universe. The telescope's work lays the groundwork for decades of astronomy, providing reference points, unexpected findings, and critical measurements that redefine what is possible in observing the universe's first billion years, and pushing humanity closer to understanding the origins and evolution of the cosmos. Collaboration with other observatories. James Webb does not work alone. Its discoveries are amplified when combined with other world-class observatories that study the universe in ways Webb cannot. And this collaboration is transforming astronomy into a truly multi-wavelength, multi-dimensional science. The Atacama Large Millimeter/Submillimeter Array, or ALMA, located high in Chile's Atacama Desert, observes the cold universe, detecting the faint glow of molecular gas and dust that forms the raw material for stars and galaxies. While Webb excels at infrared light, tracing the heat from early stars and galaxies, ALMA provides complementary information about the cold gas reservoirs from which those stars were born, mapping how matter is distributed in the earlier structures and how it flows into forming galaxies. Observing the same objects with Webb and ALMA allows scientists to compare stellar activity with the surrounding gas, revealing how the first galaxies converted raw material into stars, and how feedback from those stars shaped their environment. Next-generation radio arrays, such as the Square Kilometre Array, SKA, and Expanded Very Large Array, VLA, instruments, add yet another layer. Radio waves can trace neutral hydrogen, the most abundant element in the universe, across vast distances and timescales. This lets astronomers study the distribution of matter on the larger scales, revealing the cosmic web, the filamentary structure of galaxies and gas stretching across billions of light years. Webb sees the early galaxies embedded in this web, but radio arrays detect the hydrogen that surrounds them, showing where matter is gathering and how it moves under gravity. Combining Webb's infrared images with radio maps allows researchers to see not only the visible galaxies, but also the invisible scaffolding that guided their formation, uncovering the dynamic interplay between luminous matter and the dark structures that dominate the universe. The Vera Rubin Observatory, designed for wide-field optical surveys, contributes another dimension, observing vast regions of the sky repeatedly over time to capture variability, motion, and large-scale structure. While Webb peers deeply into small regions for faint, high redshift objects, Rubin surveys cover thousands of square degrees, finding clusters, supernova, and transient events. Rubin's optical data provides context for Webb's detailed infrared snapshots, identifying regions of interest and capturing phenomena like gravitational lensing, where massive galaxies bend light from even more distant objects, magnifying them so Webb can study them in unprecedented detail. Lensing is crucial for early universe research because it allows astronomers to detect faint galaxies that would otherwise be invisible, stretching the reach of Webb even further into cosmic history. Together, Webb, ALMA, Rubin, and next-generation radio arrays create a network of observatories that covers nearly the entire electromagnetic spectrum, from radio waves through millimetre and sub-millimetre bands, through optical and infrared, and into the mid-infrared. Each wavelength tells a different story. Infrared light reveals heat from stars, sub-millimetre light traces cold gas and dust, optical light shows stars and clusters in visible detail, and radio waves map hydrogen and magnetic fields across vast scales. The combination provides a holistic view of the early universe, allowing astronomers to connect the dots between raw material, star formation, galaxy assembly, and large-scale cosmic structure. Collaboration also allows for precise timing and repeated observations. Webb can identify a distant galaxy with unusual chemical signatures or extreme star formation, and ALMA can follow up to measure cold gas content and dynamics. Rubin can provide the broader context, showing how that galaxy fits within larger structures, while radio arrays trace the surrounding hydrogen to understand its environment. This coordinated effort creates a multi-layered data set, where every instrument contributes a different perspective, revealing processes that operate on scales from individual stars to the cosmic web. By combining data across observatories, scientists can test fundamental cosmological theories more rigorously than ever before. For example, early galaxies discovered by Webb can be compared with hydrogen maps from radio arrays to see whether the observed distribution of matter matches predictions from inflationary models. ALMA's data on molecular clouds can show whether star formation rates correspond to the growth patterns inferred from Webb's infrared observations. Rubin Observatory's optical surveys track how galaxies cluster over time, providing a larger scale perspective that contextualizes Webb's narrow but deep fields. Each observatory strengthens the conclusions drawn from the others, creating a cross-validated understanding of the universe's formative periods. These collaborations also enhance efficiency and discovery potential. Webb can focus on deep, high-resolution observations of the most distant galaxies, while Rubin identifies large regions with high potential for unusual or extreme objects. ALMA measures the physical state of cold gas that fuels early stars, and radio arrays map hydrogen to reveal unseen cosmic structures. Together, these observatories allow scientists to design observations strategically, targeting regions where multiple instruments can collect complementary data simultaneously, reducing uncertainty and maximizing the information returned from each precious hour of observation. In practice, a single discovery might involve data from all 4 observatories. Webb detects a faint, red-shifted galaxy in the infrared, revealing early star formation and chemical composition. ALMA measures surrounding cold gas and dust, showing where future stars may form and how feedback from existing stars affects the environment. Rubin Observatory provides a wider field optical view, revealing neighbouring galaxies and gravitational lensing effects that enhance detection of faint features. Radio arrays map the hydrogen surrounding the galaxy, indicating the larger scale cosmic structure that feeds its growth. Each dataset alone is informative, but combined, they tell the full story of how the galaxy formed, how it interacts with its surroundings, and what it reveals about the early universe. Collaboration between these observatories also enables cross-validation of unexpected phenomena. Webb may detect a galaxy with unusual brightness or chemical abundance, raising questions about early star formation or inflation. ALMA's observations of cold gas can confirm whether such rapid formation is feasible. Rubin's optical surveys may show neighbouring galaxies interacting or merging, providing a natural explanation for the anomaly. Radio arrays can reveal whether hydrogen flows or density variations support the observed structure. This multi-instrument approach allows scientists to separate real cosmic features from observational artifacts and ensures that surprising discoveries withstand rigorous scrutiny. The synergy between Webb and other observatories is also essential for mapping cosmic evolution over time. Webb's deep field observations show how the earliest galaxies appear and evolve, while Rubin's repeated optical surveys track changes in brightness and motion across broader scales. ALMA provides chemical and physical details about interstellar gas, and radio arrays trace large-scale structure. Together, these datasets form a timeline of cosmic history, revealing how matter coalesced into galaxies, how star formation progressed, and how energy flowed through space during the universe's first billion years. This multi-observatory approach is pushing astronomy into a new era, where discoveries are no longer based solely on single telescope data. Instead, every observation can be contextualized across wavelengths and scales, uncovering relationships that would remain hidden without collaboration. Webb's infrared vision identifies the earliest structures. ALMA measures the raw materials. Rubin reveals the broader landscape, and radio arrays trace the invisible scaffolding of hydrogen and cosmic filaments. Each discovery becomes part of a coordinated effort to understand the universe as a connected system rather than isolated snapshots. Future discoveries are expected to rely heavily on this collaborative framework. Teams are designing coordinated surveys where Webb, ALMA, Rubin, and next-generation radio arrays observe overlapping regions, building datasets that capture structure, chemistry, energy, and motion all at once. This approach will allow astronomers to investigate the mechanisms that shape the first galaxies, identify regions where inflation or other early universe processes left detectable imprints, and explore how matter and energy distributed themselves across the cosmos in the moments after the Big Bang. Multi-observatory collaboration also enables rapid response to surprises. If Webb detects a galaxy that appears too massive or chemically evolved for its time, ALMA can follow up with gas measurements. Rubin can examine nearby objects for interactions, and radio arrays can map the surrounding hydrogen environment. This coordinated effort ensures that extraordinary discoveries are verified, analysed in context, and integrated into our understanding of the universe quickly and accurately. Expected breakthroughs. James Webb is set to deliver discoveries that will redefine what we know about the universe, opening windows into mysteries that have puzzled astronomers for decades. One of the most tantalizing areas is dark matter, the invisible substance that makes up the majority of the universe's mass yet cannot be seen directly. Webb's deep field observations allow scientists to trace how galaxies formed and clustered in the earliest epochs, revealing patterns that correspond to the underlying distribution of dark matter. When galaxies appear in unexpected locations, or when the density of matter does not match predictions, it offers clues about how dark matter behaves, how it interacts gravitationally with visible matter, and how it guided the formation of the first cosmic structures. Combining Webb's infrared imaging with data from gravitational lensing, where massive foreground galaxies bend light from more distant objects, helps map the shape and concentration of dark matter across space, giving an indirect but remarkably detailed view of its influence in the early universe. Cosmic inflation, the explosive expansion that occurred in the universe's first fractions of a second, is another focus. Webb may detect subtle imprints left by this rapid growth, recorded in the arrangement of the earliest galaxies and the faint light of primordial gas clouds. Slight variations in density, chemical composition, or motion within early galaxies could provide evidence of quantum fluctuations that seeded the universe's large-scale structure. Webb's instruments, working together, capture the light from these ancient objects with incredible precision, allowing scientists to identify patterns that hint at the mechanisms behind inflation. These observations can test theoretical predictions about how the universe grew from a nearly uniform field into the complex cosmic web observed today. Star formation in the early universe is also coming under scrutiny like never before. Webb can detect the first generations of stars, including population 3 stars, which are believed to contain only hydrogen and helium. These stars are critical for understanding the early enrichment of the universe with heavier elements. Spectroscopy can reveal the chemical fingerprints of these early stars, while infrared imaging identifies the dense gas clouds in which they formed. Scientists are looking for regions of rapid star formation, unexpected stellar masses, and bursts of activity that suggest stars were forming faster and more efficiently than previous models allowed. Webb's observations will reveal not just when the first stars ignited, but how they influenced surrounding gas, triggered subsequent generations of stars, and contributed to reionization, the process that made the universe transparent to light. Black holes in the early universe are another area where breakthroughs are expected. Webb can detect the infrared glow from accreting black holes, even when shrouded by dust, and can identify the earliest supermassive black holes, which appear to have grown extremely rapidly after the Big Bang. Observing the properties of these early black holes, their masses, growth rates, and interactions with surrounding galaxies provides insight into how they formed and how they shaped galaxy evolution. Webb's combination of imaging and spectroscopy allows astronomers to measure radiation output, chemical enrichment, and feedback effects, showing how early black holes influenced star formation and redistributed gas and energy in their host galaxies. These observations challenge conventional models of black hole formation, offering a window into the extreme physics of the early universe. Webb is also expected to reveal connections between these phenomena, showing how dark matter, inflation, star formation, and black holes interacted in the first billion years. Early galaxies are not isolated. They form in dense environments shaped by gravity and energy flows, and Webb's multi-instrument observations can map these interactions. Spectroscopy identifies chemical composition and motion. Imaging reveals structure and morphology, and mid-infrared observations detect dust-enshrouded regions, producing a full picture of how matter and energy evolve together. These connections provide insight into why the universe looks the way it does today, showing how the earliest processes set the stage for the complex structures we observe across cosmic time. Unexpected phenomena may emerge as well, such as galaxies or star clusters that formed earlier or faster than anticipated, regions with unusual chemical enrichment, or energy signatures that hint at unknown physics. Webb's sensitivity allows the detection of faint and distant objects, increasing the chances of observing rare events that challenge existing theories. These discoveries could reveal processes that operated in extreme conditions, such as rapid star formation, early black hole mergers, or interactions between galaxies that shaped growth in surprising ways. Each anomaly is an opportunity to refine models of the universe and to explore aspects of physics that cannot be replicated in laboratories on Earth. The synergy of Webb's instruments plays a crucial role in these breakthroughs. NIRCam reveals structure and faint light from distant objects. NIROSPEC measures chemical composition and velocities, MyRI detects dust and cooler regions, and NIRES provides additional spectral data and guidance. Together, these instruments capture multi-dimensional information for every object, allowing astronomers to reconstruct the physical, chemical, and dynamical history of galaxies, star clusters, and black holes in the early universe. This level of detail is unprecedented and enables investigations into questions that have remained unanswered for decades, from the behavior of dark matter to the origins of cosmic inflation. Webb also enables precise measurements of cosmic timelines. By observing galaxies at different redshifts, scientists can track the evolution of structure, the buildup of chemical elements, and the growth of black holes. These measurements refine models of star formation rates, galaxy assembly, and feedback processes, creating a detailed chronology of the universe's first billion years. Understanding the timing of these events is critical for testing theories about inflation, the formation of the first stars, and the emergence of large-scale structures, and Webb's multi-wavelength data provides the resolution and depth needed for accurate reconstruction. Collaboration with other observatories strengthens these breakthroughs further. ALMA reveals the cold gas fueling star formation, radio arrays trace hydrogen and the cosmic web, and optical surveys from Vera Rubin Observatory provide context on large-scale clustering and transient events. Webb's infrared data, combined with these complementary observations, offers a holistic understanding of the early universe, where every galaxy, cloud, and black hole is mapped within its cosmic environment. This collaboration allows scientists to confirm discoveries, cross-validate unexpected phenomena, and reveal connections between structure, chemistry, and energy that are invisible to any single observatory. Breakthroughs from Webb will reshape theories across astronomy. Models of dark matter distribution can be tested against observed galaxy clustering. The timing and scale of inflation can be inferred from early structures. Star formation physics can be studied in pristine conditions, and the growth of early black holes can be directly measured. Each discovery informs multiple areas simultaneously, showing how interconnected cosmic processes are. Webb's observations do not simply add new data, they open entirely new dimensions of understanding, allowing scientists to probe the universe in ways that were impossible before. These expected breakthroughs are not limited to confirming existing theories. They also expand the frontier of questions that can be asked. Observations of unusual galaxies, unexpected chemical abundances, extreme energy outputs, and surprising interactions may reveal unknown mechanisms of cosmic evolution. Webb's combination of sensitivity, resolution, and wavelength coverage allows the detection of objects and phenomena that are extremely faint, extremely distant, or hidden by dust, creating opportunities for discoveries that could rewrite textbooks. Each breakthrough adds a piece to the puzzle, connecting dark matter, inflation, star formation, and black holes into a cohesive narrative of how the universe grew from its earliest moments. The full potential of these discoveries emerges when data is analysed across multiple objects and regions. Webb surveys identify trends, patterns, and anomalies, revealing how early galaxies relate to one another and to the larger cosmic environment. Dark matter structures, the timing of star formation, the chemical enrichment of gas clouds, and the growth of black holes are all studied in concert, providing a comprehensive view of the universe's formative processes. Webb allows astronomers to not only observe the distant universe, but to understand the relationships that drive its evolution, linking microscopic physics in stars to macroscopic cosmic structure. Every observation pushes boundaries, revealing the interplay between matter, energy, and gravity across the first billion years. Webb's instruments capture structure, chemistry, temperature, motion, and radiation simultaneously, producing datasets that are unparalleled in detail and scope. These observations directly probe fundamental questions. How did the first galaxies assemble? How did dark matter guide their growth? How did the first stars form and evolve? And how did black holes emerge and influence their surroundings? Webb makes it possible to address these questions with empirical evidence rather than theoretical speculation, providing a roadmap for the next generation of astronomy. The combination of deep field imaging, spectroscopy, mid-infrared sensitivity, and collaboration with other observatories ensures that every aspect of the early universe is explored. Webb's observations illuminate the distribution of matter, the flow of energy, the formation of stars, the growth of black holes, and the imprint of cosmic inflation across space and time. Expected breakthroughs will not only confirm what scientists suspect, but reveal phenomena that were previously hidden, uncovering new processes and relationships that expand the scope of cosmic understanding. Each photon captured contributes to a larger narrative, showing how the universe evolved from a nearly uniform state into the complex tapestry of galaxies, stars, and black holes seen today. Webb's discoveries create a foundation for decades of future research. Astronomers can follow up with targeted observations, multi-wavelength campaigns, and theoretical modelling, connecting the earliest cosmic structures to the physics of star formation, galaxy evolution, and black hole growth. The telescope's ability to see faint, distant, and dust-obscured objects enables studies that were impossible with previous observatories, providing empirical data to test and refine models across the fields of cosmology, astrophysics, and high-energy astronomy. This depth of observation ensures that every discovery contributes to a coherent, detailed, and multi-dimensional understanding of the early universe. Expected breakthroughs from Webb promise to reveal the processes that shape the universe's infancy, from the subtle effects of dark matter to the explosive formation of the first stars and black holes, while providing insights into the mechanisms that govern cosmic inflation and the emergence of structure. Webb's multi-instrument approach, combined with collaborations across observatories and wavelengths, allows scientists to piece together a complex story that spans billions of years, transforming faint signals into a rich map of the universe's origins, growth, and evolution. JWST and the questions once thought impossible. The James Webb Space Telescope is doing something that no other telescope has ever done before. It is reaching into the universe's earliest moments, capturing light that has travelled for billions of years, stretching from the birth of the first stars and galaxies into our telescopes. For decades, astronomers have had to make educated guesses about the very first objects, the triggers of cosmic inflation, and the way the universe grew from a singularity into the vast web of galaxies we see today. Many of these questions were considered almost impossible to answer because the signals were faint, buried under noise, or hidden behind clouds of gas and dust. Webb changes all of that. Infrared light, the kind Webb specializes in, carries information from objects so distant and faint that they were invisible to Hubble or Spitzer. It allows scientists to see the first stars forming inside clouds of hydrogen and helium, galaxies emerging when the universe was only a few 100 million years old, and energy signatures that could reveal processes no one had observed directly before. Some of these signals are faint whispers from the past, almost drowned out by background noise or cosmic interference, and separating what is real from what is an artifact is a constant challenge. Every photon Webb captures is precious, and every spectrum has to be analysed carefully to ensure it represents an actual cosmic process, and not a glitch in the instruments or a misinterpretation caused by the limits of current technology. Signal to noise is one of the biggest hurdles. Early galaxies emit incredibly faint light, and by the time that light reaches Webb, it has been stretched and dimmed by billions of years of cosmic expansion. Detecting these photons requires long exposure times, careful calibration, and extremely stable pointing to avoid blur or distortion. Even with Webb's sensitivity, there are uncertainties. A galaxy that appears bright in one wavelength may be nearly invisible in another. Spectral lines indicating chemical composition may be shifted or blended, making it difficult to distinguish whether the signal comes from a primordial star, a dust cloud, or background contamination. Researchers have to cross-check observations across multiple instruments and revisit targets with repeated exposures to confirm findings, combining NIRCAM, NIRS-PEC, MIRE, and NIRACE data to create a coherent picture of what is happening in these early objects. This raises questions about interpretation. Could some of the extraordinary signals Webb is detecting be misread? A galaxy appearing unusually massive or bright might, in reality, be a blend of multiple smaller galaxies aligned along the same line of sight. Unusual chemical abundances could result from overlapping spectra or instrumental artifacts. Scientists spend months examining data to rule out these possibilities, using simulations and comparisons with other observatories to verify that what Webb sees corresponds to real cosmic structures. Collaboration with ALMA, Vera Rubin Observatory, and next-generation radio arrays strengthens confidence as each observatory observes the same regions in different wavelengths, confirming or challenging Webb's interpretations. Despite these challenges, Webb is achieving what once seemed impossible. It is providing direct evidence of objects from the first billion years, detecting galaxies that should not exist according to previous models, measuring chemical fingerprints from stars that formed before heavier elements were abundant, and tracing energy flows that could indicate early black holes or bursts of star formation. Every discovery forces astronomers to examine whether their previous assumptions about galaxy formation, cosmic inflation, or the timing of structure formation are correct. Some results align with predictions, others contradict them, and some fall into entirely new territory, hinting at processes never before considered. The telescope also faces limitations from cosmic variance and sample size. Observing a few distant galaxies does not automatically represent the entire early universe. Light from the farthest objects travels along paths shaped by gravity and cosmic expansion, sometimes magnifying or distorting what we see. Signal faintness, background interference, and instrumental noise all add uncertainty, which means interpretations must be cautious. Scientists often compare Webb's observations with simulations and previous surveys, like those from Hubble or Planck, to determine whether a finding is truly unprecedented or a statistical anomaly. Even when the data are strong, the extraordinary distances and faintness push the limits of what can be concluded with certainty. Yet it is precisely these challenges that make Webb's mission revolutionary. Questions that were previously theoretical are now within reach of observation. Was there a specific trigger for inflation? How fast did the first stars and galaxies form? Did black holes appear almost immediately after the first stars, or did they grow more slowly? How did matter, dark matter, and energy interact in the universe's first moments? Each of these questions relies on detecting incredibly faint signals and interpreting them correctly, and Webb's combination of instruments, sensitivity, and collaboration with other observatories allows scientists to approach answers in ways that were unthinkable only a few years ago. Observations that seem impossible to confirm are becoming possible because Webb captures light with such precision that even subtle features, like the faint glow of hydrogen gas or the chemical fingerprints of early stars, can be measured and analysed. Spectra reveal the velocity of gas, the presence of metals, and the temperature of stellar nurseries. Imaging shows the structure of galaxies forming just a few 100 million years after the Big Bang. Mid-infrared observations detect dust and hidden energy, adding detail to a picture that previously existed only in simulations. Every dataset provides multiple angles on the same object, increasing confidence that the signals correspond to real, physical phenomena, and not errors or misinterpretations. At the same time, scientists remain cautious. Extraordinary discoveries are scrutinized, repeated, and cross-checked. Webb observations must be carefully compared with models, and anomalies require careful study to determine whether they reveal new physics or are artifacts of observation. The very faintness of early universe signals means that small errors can lead to big misinterpretations, and every claim is tested rigorously. This caution does not slow the pace of discovery. It ensures that each finding is robust and can be trusted as a building block for understanding the cosmos. The possibility of misinterpretation does not diminish the excitement. Even when signals are uncertain, they point toward areas where breakthroughs could occur. Every faint galaxy, every unusual spectrum, every pattern of energy captured in the early universe provides clues about processes once considered beyond reach. Webb allows scientists to explore the boundary between what is known and what is hypothesized, offering glimpses into the earliest moments of cosmic history, the first stars, the birth of galaxies, and the dynamics that shaped the universe long before our solar system existed. In some ways, the challenge of interpreting Webb's data mirrors the challenge of exploring the universe itself. The first photons from distant galaxies carry answers wrapped in billions of years of cosmic history, and separating those answers from noise, distortion, and instrumental limits requires patience, ingenuity, and collaboration. Webb has provided the tools to tackle these challenges, and astronomers are discovering that questions once considered impossible to answer can now be addressed, even if cautiously, even with careful cross-checking, and even while acknowledging the limitations imposed by distance, faintness, and signal to noise. The telescope is rewriting the playbook for what can be observed. What was previously theoretical speculation about the first stars, the earliest galaxies, and the triggers of cosmic inflation is now grounded in observation, even if confirming the details takes time. The interplay between potential misinterpretation and extreme sensitivity pushes scientists to develop new techniques, test models in new ways, and collaborate across multiple instruments and observatories to ensure the universe is telling its story accurately. JWST has opened a window where the faintest, oldest light can be studied with unprecedented clarity, and that clarity allows astronomers to pursue answers that were once off limits, while still navigating the uncertainties inherent in exploring billions of light years into the past. Signal-to-noise challenges, instrumental limitations, and the faintness of ancient light create a landscape where discoveries must be carefully interpreted. Yet every photon captured adds to a growing understanding of how the universe began, how the first structures formed, and what processes may have triggered the events that shaped everything that followed. Even when observations seem ambiguous, they guide scientists toward new methods and new hypotheses. Detecting a faint galaxy, analyzing its spectrum, and comparing it with other instruments pushes the boundaries of what is knowable. Each potential misinterpretation sparks deeper analysis, more refined observation techniques, and cross-wavelength studies that reveal hidden truths. Webb's unprecedented sensitivity makes it possible to see these features at all, and its ability to combine data from multiple instruments and observatories provides the checks needed to separate real signals from noise. Through this process, the telescope transforms questions that once seemed impossible into researchable mysteries. Scientists can test ideas about the first stars, the origin of galaxies, early black holes, and cosmic inflation in ways that were previously speculative. Every careful observation, repeated measurement, and comparison across instruments narrows uncertainty, strengthens confidence, and provides the first glimpses of phenomena that existed when the universe was still in its infancy. JWST is turning theoretical speculation into observable science, giving astronomers the ability to explore processes that once could only be imagined. Alternative explanations and media hype. When James Webb captures a signal from the early universe that looks extraordinary, it's tempting to immediately link it to the origin of everything, as if the telescope has revealed the moment the Big Bang was triggered. Scientists, however, move with caution. The universe is a tricky place, and multiple phenomena can create signals that resemble something groundbreaking, but have more mundane explanations. For example, a dense cluster of early galaxies might appear unusually bright in infrared, suggesting rapid star formation or an extreme energy event. But what Webb observes could actually be overlapping galaxies along the line of sight, gravitational lensing that magnifies their light, or even dust heated by stars that inflates the apparent brightness. Each observation is like a cosmic puzzle, where the first impression can be misleading, and only careful analysis across instruments and wavelengths can reveal what is really happening. Exotic energy events, like quasars or early black holes, also emit light that could be mistaken for primordial triggers. A quasar at high redshift produces enormous amounts of radiation as gas spirals into a supermassive black hole, and this radiation can mimic the signatures expected from processes connected to inflation or the first generation of stars. Similarly, supernovae in young galaxies, exploding at rates much higher than in the modern universe, create flashes of energy and chemical enrichment that could be misinterpreted as evidence for unusual early universe phenomena. Webb's multi-instrument approach helps distinguish these possibilities by analysing spectra, measuring chemical composition, and observing structure. But it requires careful modelling and comparisons with other observatories like ALMA, Rubin, and next-generation radio arrays to eliminate alternative explanations. Cosmic variance also contributes to potential misinterpretation. The universe is not uniform on small scales, and early structures are patchy. Detecting a particularly bright or dense region does not necessarily represent a universal process. It may be a rare anomaly. This means scientists must gather multiple observations across different regions to ensure that what they see is part of a broader pattern and not a cosmic fluke. Each field observed by Webb is like peering through a keyhole into the universe, and drawing bold conclusions without additional evidence can lead to misunderstandings. Despite this complexity, media headlines often simplify discoveries into digestible, sensational statements. Stories claiming that Webb found what triggered the Big Bang or solved the universe's greatest mystery spread quickly, but the reality is far more nuanced. Scientific papers report tentative results, carefully noting limitations, uncertainties, and the need for follow-up studies. Journalists frequently condense these details, emphasizing excitement and novelty over caveats, creating hype that can outpace the science. The result is a gap between what Webb actually observes and what the public reads, giving the impression that the universe's origin has been fully revealed when the telescope has only provided tantalizing hints. The way headlines frame discoveries can affect public perception, influencing how people think about astronomy and cosmology. A complex analysis of spectral lines, redshifts, and multi-instrument observations is compressed into a few dramatic words, emphasizing immediate significance rather than the process of careful validation. Scientists are aware of this, and many take the time to clarify that what Webb detects is evidence of early universe phenomena, not a direct measurement of the Big Bang trigger. Yet the allure of a first detection makes it difficult to balance accuracy with storytelling, especially in an age where attention is fleeting and dramatic phrasing spreads rapidly online. The debate over discovery headlines also underscores the challenge of interpreting Webb's data in real time. Some signals may be misread initially, prompting corrections or reinterpretations as more observations come in. A galaxy thought to be exceptionally massive may later be resolved into multiple objects, or an unusual energy signature may be attributed to dust rather than an extreme event. Each refinement demonstrates the difficulty of drawing final conclusions from data that push the limits of detection and the importance of cross-checking with other observatories. Alternative phenomena complicate claims of detecting a Big Bang trigger, but they also enrich the scientific process. By considering other explanations, supernovae, quasars, overlapping galaxies, dust, gravitational lensing, researchers ensure that interpretations are robust. Webb's ability to capture multiple wavelengths simultaneously, combined with follow-up observations, allows these alternative scenarios to be tested and eliminated. Scientists compare infrared brightness with chemical composition, check structural details against lensing models, and examine surrounding gas with ALMA or hydrogen maps from radio arrays. The process transforms apparent anomalies into deeper understanding of how the early universe actually behaved. The interplay between discovery, interpretation, and media hype illustrates how science communicates in the modern era. Webb's images and spectra are mesmerizing, and the temptation to assign cosmic significance to every observation is strong. Scientists must balance the excitement of pushing observational frontiers with the careful work of verifying signals, ruling out alternative phenomena, and constructing narratives that match evidence. Media coverage amplifies both the excitement and the confusion, highlighting discoveries in bold terms while often skipping the nuances, leading to headlines that can misrepresent the nature of the findings. Despite these challenges, the dialogue between researchers and the public is valuable. Headlines spark curiosity and interest in astronomy, encouraging people to learn about concepts like redshift, infrared light, and early galaxy formation. Webb's discoveries, even when initially misinterpreted, create opportunities for education, discussion, and a broader appreciation of the universe's complexity. Misinterpretations, alternative explanations, and media simplifications all form part of the process by which knowledge advances, as scientists refine models, gather additional data, and clarify findings for the world. Webb's mission demonstrates the fine line between detection and interpretation. Every faint galaxy, every unusual spectrum, and every distant energy signature could either reveal a profound insight or reflect a more common astrophysical process. Alternative explanations ensure that scientists do not jump to conclusions, while careful analysis across instruments and observatories helps separate genuine early universe phenomena from artifacts, coincidences, or misleading appearances. This balance between caution and exploration defines the cutting edge of modern cosmology. Ultimately, Webb captures signals that were previously out of reach, signals that could contain clues to the universe's earliest events. Some of these signals might mimic a Big Bang trigger or hint at unknown energy phenomena, and the challenge is to determine which is which. The telescope's sensitivity, combined with multi-instrument and multi-observatory collaboration, allows these signals to be studied with unprecedented precision, separating the cosmic story from noise, chance alignment, or misleading appearances. Every observation is examined critically, compared across wavelengths, and tested against models to ensure that what is reported reflects real phenomena rather than a superficial reading. The debate over headlines and alternative explanations also emphasizes how remarkable Webb's capabilities are. Few instruments in history have been able to capture such faint, distant light, while resolving details of structure, motion, and chemical composition. Even when interpretations are debated, the fact that Webb provides data that can test hypotheses once considered unobservable is extraordinary. Researchers now have tools to study the first galaxies, the earliest stars, and the mechanisms that may have driven inflation, all while navigating signal-to-noise challenges and the possibility that some observations could be misleading. Reconstructing the first moments. The universe begins in a fraction of a second, a spark of creation that scientists call the Big Bang. But that name hides more complexity than most people realize. Imagine a state where time, space, and matter are compressed into a point so dense and hot that conventional physics breaks down. In that first instant, the universe is not expanding gently. It's inflating at an unimaginable speed, stretching space-time itself faster than light, creating tiny variations in density and energy that will become the seeds of every star, every galaxy, every structure that follows. These fluctuations are almost imperceptible, microscopic differences in an otherwise uniform field, but they are crucial because they determine where matter will clump, where gravity will pull, and where the first cosmic structures will take shape. These fluctuations are quantum in nature, arising from the fundamental uncertainty of energy and fields at the smaller scales. For decades, scientists could only model this period with equations and simulations, imagining how inflation would imprint subtle patterns that could survive billions of years. After inflation, the universe cools slightly and matter begins to separate from radiation. Hydrogen and helium dominate, and the first clouds of gas form in the densest regions of space. These primordial clouds are the birthplaces of the first stars, often called population 3 stars. Unlike stars today, these pioneers contain almost no heavier elements, no metals, just pure hydrogen and helium. They burn hot and fast, illuminating the darkness for the first time and shaping the surrounding gas with their radiation. These stars are fleeting in cosmic terms, yet their existence triggers a chain reaction. They create the first heavy elements through nuclear fusion, enrich their surroundings when they explode as supernovae, and pave the way for the second generation of stars and galaxies. Without this first wave of stars, the universe would remain dark and lifeless for much longer, leaving no structures to observe, no clues for scientists to reconstruct its earliest history. James Webb adds a new layer to this narrative. Unlike previous telescopes, it can peer into the infrared, capturing light that has been stretched over billions of years. That light carries direct information about these first stars and galaxies, energy fields in the early universe, and structures that formed just a few 100 million years after the Big Bang. When Webb observes a faint, red-shifted galaxy, it is not just seeing a dot of light, it is seeing the cumulative imprint of density fluctuations, star formation, and early chemical enrichment. NIR-CAM can detect the overall structure and morphology. MIRI reveals dust and cooler regions, and NIR-SPEC identifies the chemical fingerprints, velocities, and temperatures of the gas and stars. Each observation is a clue, a fragment of a puzzle that traces back to the universe's first moments. The visualization of the first seconds and minutes after the Big Bang is almost beyond imagination. Energy fields ripple through space, quantum fluctuations create tiny peaks and valleys, and radiation dominates the environment. These fields are chaotic, but patterned, leaving subtle imprints that persist through time. Even as matter begins to coalesce and the universe cools, those primordial variations shape the distribution of gas and dark matter, guiding the assembly of the earliest galaxies. Detecting these imprints directly would have been impossible without instruments capable of resolving extremely faint light at high redshift. Webb provides a bridge between theoretical models of this period and observable reality. What was once a set of equations and computer simulations now has empirical support through actual measurements of light, chemical composition, and galactic structure. Piecing the puzzle together requires more than just observation. Theoretical physics predicts how inflation operates, how quantum fluctuations grow, and how energy propagates in the early universe. Cosmology provides the framework to link these predictions with the large-scale distribution of matter, the growth of galaxies, and the evolution of cosmic structures. Observational astronomy supplies the data, the photons from the first galaxies and stars, and the spectral information that reveals chemical composition, motion, and energy output. Scientists combine these strands, checking whether the patterns predicted by theory match what Webb actually sees. Discrepancies are just as important as matches because they highlight areas where understanding is incomplete or where the universe behaves in unexpected ways. Every faint galaxy observed with Webb becomes a time capsule carrying information about early density fluctuations and chemical composition. The shape and distribution of stars within these galaxies reveal the intensity of star formation, the influence of radiation from previous generations, and the dynamics of gas within gravitational wells created by dark matter. Spectroscopic analysis identifies elements and traces ionization states, showing how the first generations of stars processed hydrogen and helium into heavier elements. By comparing these observations across multiple galaxies, astronomers can reconstruct the overall timeline of early structure formation, seeing how matter assembled into stars, clusters, and eventually galaxies. Quantum effects, once confined to abstract equations, leave observable footprints that Webb can detect indirectly. Tiny variations in density and temperature affect the light emitted by the first stars and galaxies, influencing the spectra and infrared brightness. These variations also guide how gas clouds collapse into stars, producing subtle differences in galaxy size, shape, and chemical distribution. By analysing these variations across multiple high redshift galaxies, scientists infer the nature of the quantum fluctuations that shape the universe, connecting the earliest moments of energy and matter to structures visible billions of years later. Density fluctuations in the early universe are not uniform. Some regions collapse faster, forming stars and galaxies sooner, while other areas remain diffuse for millions of years. Webb can detect these differences, revealing pockets of accelerated formation or unusually massive early galaxies. This information is crucial for testing models of cosmic inflation and for understanding the interplay between dark matter, radiation, and baryonic matter in shaping cosmic structures. Observations of clustered or unusually bright early galaxies hint at regions where fluctuations were particularly pronounced, providing a glimpse into the raw initial conditions from which the universe evolved. The first stars illuminate their surroundings, generating ultraviolet radiation that ionizes hydrogen in nearby clouds. This process, called reionization, transforms the universe from opaque to transparent, allowing light to travel freely. Webb observes galaxies and gas clouds in this transitional period, providing insight into the timeline and intensity of reionization. Spectroscopic measurements reveal the fraction of neutral hydrogen remaining, the temperature of ionized gas, and the influence of early stellar populations. These measurements trace the interaction between radiation and matter, showing how energy released by the first stars reshaped the universe on large scales. Reconstructing the cosmic story also involves tracking early black holes. Some of the first stars collapse directly into black holes, while others form seeds that grow rapidly through accretion and mergers. Webb can detect the infrared glow from these early black holes, even when shrouded by dust, and can measure their influence on surrounding galaxies. Observations of active galactic nuclei in high redshift galaxies reveal energy outputs that affect star formation and gas distribution, linking the growth of black holes to the broader cosmic environment. These connections help scientists understand how matter, energy, and gravity interacted during the universe's formative years. Every discovery adds a piece to a timeline stretching from the first moments of inflation to the assembly of the first galaxies. By observing multiple wavelengths, scientists can separate stars from dust, identify chemical abundances, and measure the motion of gas. Webb's multi-instrument data allows researchers to create a layered view of the early universe, where light, matter, and energy interact across scales ranging from individual stars to entire proto-galaxies. This layering is essential for reconstructing the sequence of events that turned a nearly uniform quantum field into a universe filled with structure, radiation, and complexity. The process of piecing together this story is iterative. Observations feed into models. Models guide new observations, and each cycle refines the understanding of the early universe. Webb allows astronomers to detect phenomena that were previously invisible, like faint population 3 star clusters, primordial gas clouds, and early black hole activity. Each detection is cross-checked with simulations, compared to other observatories, and analysed for alternative explanations. This detective work requires meticulous attention to detail, patience, and a willingness to challenge assumptions, because the universe does not present its history neatly. It is layered, complex, and full of surprises. Scientists also analyse spatial distributions. How are early galaxies clustered? Where does star formation appear concentrated? Do certain regions show unusual chemical enrichment? Webb's imaging provides detailed maps of these early structures, revealing the imprint of inflation and the effects of quantum fluctuations. Spectroscopy adds a third dimension, showing velocities, temperatures, and element abundances. This combination produces a multi-dimensional view of the universe as it evolved, allowing researchers to reconstruct events that occurred when the universe was only a fraction of its current age. Observations of cosmic filaments, the large-scale web of matter that stretches across space, help scientists connect small-scale structures to the overall distribution of matter. Webb detects the faint glow of early galaxies along these filaments, showing how gravitational forces shape the arrangement of matter. This structure traces back to the density fluctuations from inflation, providing a visual and measurable link between the earliest moments and the organization of galaxies. By studying the patterns of matter distribution, researchers test theories of dark matter behavior, energy propagation, and the physics of cosmic expansion. The telescope's data also illuminate chemical evolution. The first stars produce elements heavier than helium, and when they die, they seed the surrounding gas with metals. Webb can detect these early enrichments, revealing which regions experienced rapid star formation and which remained pristine. Observing variations in chemical composition across different galaxies and protoclusters allows astronomers to reconstruct the timeline of element formation and distribution, connecting nuclear processes inside stars to the growth of galaxies on cosmic scales. By combining theoretical physics, cosmology, and observational astronomy, scientists reconstruct the sequence of events from the Big Bang through inflation to the first stars. Each faint photon, each spectral line, and each structural detail contributes to a coherent story of how energy, matter, and gravity interacted in the universe's infancy. Webb makes it possible to measure these phenomena directly rather than relying solely on simulations or indirect inference, creating a bridge between abstract theory and observable reality. JWST allows researchers to explore phenomena that were previously invisible. It detects gas clouds that have never formed stars, faint galaxies barely brighter than the background, and unusual energy signatures from early black holes or quasars. Each observation provides a clue, and assembling these clues requires analysing multiple instruments, checking alternative explanations, and synthesizing information across wavelengths. The telescope transforms the reconstruction of the first moments into a dynamic, empirical process, where theoretical predictions meet real data, producing a narrative of cosmic evolution rooted in observation.